Procedure. A. Cleaning of platinum wire. Take a short length of platinum wire. Its one end is fused in glass rod and acts as a handle. Take about 2 milliliter of concentrated hydrochloric acid, pure, in a watch glass and dip the platinum wire in it. Do not dip platinum wire directly in the bottle. Heat the wire strongly in the non-luminous Bunsen flame till it gets red hot. If the flame gets colored, remove the wire and again dip it in concentrated hydrochloric acid. Again heat the wire to red heat. Repeat the procedure a number of times till the color of flame does not change with the introduction of wire. B. Dressing of salt. If the salt is in the form of crystals, grind it into a fine powder. Place about 1/10 gram of the powdered salt in another watch glass. Do not sprinkle salt into the flame of the Bunsen burner. C. Performing of test. Dip the clean platinum wire in concentrated hydrochloric acid, which is pure, and then roll its tip in the powdered salt, such that some of the salt sticks to its end. Introduce the tip of platinum wire in non-luminous Bunsen flame. Hold the wire in the flame till it gets red hot. Observe the color of the flame with unaided eye. Following observations will help you to identify the cation present in salt. Color of flame is intense golden yellow color with unaided eye. The color of flame is persistent. Inference: sodium ion is present. The color of flame is lilac or violet to unaided eye. The color of flame is non-persistent. Inference: potassium ion is present. The color of flame is brick red to yellowish red. The color of flame is non-persistent. Inference: calcium ion is present. The color of flame is green. The color of flame is non-persistent. Inference: copper second ion is present. To determine percentage composition of a mixture of common salt and washed coarse sand. Apparatus required: 2 beakers of 250 ml, glass funnel, glass rod, filter paper, Bunsen burner, tripod stand, wire gauge, distilled water, china dish, iron stand, physical balance, pre-weighed mixture of sand and common salt. Procedure: take a 250 ml beaker with pre-weighed mixture. Add to the mixture 100 ml of water and stir well with glass rod. Allow the mixture to settle for a minute. Pour off the clear solution in another 250 ml beaker, taking care that no grain of sand gets decanted off. Now, take a filter paper and 4-fold it, taking 3 folds to one side and 1 fold to other side. make a cone out of it. Fix the filter paper cone in a glass funnel. Fix the funnel in an iron stand and under it place a beaker. Pour off the mixture of sand and water in the funnel. Wash the beaker with about 20 ml of water and transfer it to funnel. Repeat the process 2 more times so that no sand grain is left in the beaker. When all the water filters out, remove the filter paper funnel and transfer it to a china dish. Heat the china dish on a Bunsen flame by using a tripod stand and a wire gauge. When the filter paper dries due to heat, remove it from the china dish. Transfer the semi-wet sand into the china dish, taking care that no sand grain remains sticking to the filter paper. Heat the sand strongly till it is completely dry. Now transfer the sand to the pan of physical balance, taking care that no grain of sand is left in the china dish. Weigh the sand accurately. Observations. Weight of mixture of sand and salt is equal to 70 gram and weight of dry sand is equal to 50 gram. Calculations. Weight of only salt is equal to 70 minus 50 gram, which is equal to 20 grams. Therefore, percentage of dry sand in mixture is equal to weight of dry sand upon weight of mixture of sand and salt into 100, which is equal to 50 by 70 into 100, which is equal to 71.42%. Therefore, percentage of salt in mixture is equal to weight of salt upon weight of mixture of sand and salt into 100, which is equal to 20 by 70 into 100, which is equal to 28.57%. 1. Identification of kinds of hardness in water. 2. Softening. Temporary hard water by boiling and permanent hard water by washing soda. 3. To show advantage of detergent over soap in washing when water is hard. Apparatus required. A rack of test tubes containing at least 6 clean test tubes, 3 100 cc beakers, Bunsen burner, glass funnel, filter paper, glass rod, wash bottle containing distilled water. Chemicals required. Soap solution, any detergent, distilled water sample A, temporary hard water sample B, permanent hard water sample C, test tube holder. Washing soda. Procedure. Note: you can prepare temporary hard water in bulk by passing carbon dioxide gas through 5 liters of lime water. Initially, the lime water will turn milky, but the milkiness will disappear on passing carbon dioxide in excess. The clear solution contains calcium hydrogen carbonate and the water is temporarily hard. 2. You can prepare permanent hard water by dissolving 1 gram of magnesium sulfate or magnesium chloride in 1 liter of distilled water. Identification of hardness of water and methods of softening the hard water. Test 1. Take 20 cc samples of water A, B and C in 3 beakers separately. Pour about 5 cc of sample A in the first test tube, 5 cc of sample B in second test tube and 5 cc of sample C in the third test tube. Pour 5 drops of soap solution in each test tube. Shake the test tube vigorously. Observation. In the first test tube of sample A, lather is produced readily. In the second test tube in sample B, no lather is produced but a white precipitate is formed. In the third test tube, sample C, no lather is produced but a white precipitate is formed. Inference. Sample A is soft water. Sample B is hard water. Its kind is not known. Sample C is hard water, but its kind is not known. Test 2. Take 2 clean test tubes. In the first test tube, pour 5 cc of sample B and in the second test tube, pour 5 cc of sample C. Hold the first test tube in the test tube holder and then heat it till the water starts boiling. Boil the water for 2 minutes. Allow the test tube to cool and then filter its contents in another clean test tube. To this add 5 drops of soap solution and then shake vigorously. Observation. The water in the first test tube sample B on boiling and then cooling readily forms lather with the soap solution. Inference. The water in sample B is temporarily hard. The temporary hardness can be removed by simply boiling the water for few minutes. Hold the second test tube in the test tube holder and then heat it till the water starts boiling. Boil the water for 2 minutes. Allow the test tube to cool and then filter its contents in another clean test tube. To this, add 5 drops of soap solution and then shake vigorously. Observation: the water in the second test tube, sample C, on boiling and then cooling does not form lather. Instead, it forms white precipitate. Inference: the water in the sample C is permanent hard. The permanent hardness cannot be removed by simply boiling the water. Test 3. Take 5 cc of sample C in a test tube and add to it a pinch of washing soda. Hold the test tube in a test tube holder and boil its contents for 2 minutes over a Bunsen flame. Allow the test tube to cool and then filter its contents. To this, add 5 drops of soap solution and then shake vigorously. Observation: the permanent hard water after boiling with washing soda, sodium carbonate, and filtration readily forms lathers with soap solution. Inference: the permanent hardness of water can be removed by boiling it with washing soda. Advantages of using detergents rather than soap for washing in hard water. Test 1. In a test tube, pour 5 cc of hard water, temporary or permanent, that is sample B or sample C. To this water, add 5 cc of soap solution and shake vigorously. Observation: a curdy white precipitate is formed. No lather is formed. Inference: soap is wasted in the form of curdy white precipitate. Soap is inefficient and cannot be used for washing clothes if the water is hard. Test 2. In a test tube, pour 5 cc of hard water, temporary or permanent, that is sample B or sample C. To this water, add a pinch of detergent powder and shake vigorously. Observation: lather is formed readily. No white precipitate is formed. Inference: as lather is formed, therefore no detergent is wasted. Detergent is efficient in washing clothes even if the water. To find the relationship between the distance of an object from a plane mirror to the distance of its image from the plane mirror. Apparatus required: wooden drawing board, white sheet of paper, common pins, plane mirror with stand, geometrical instruments, and a sellotape. Procedure: fix a white sheet of paper on the wooden drawing board with the help of sellotape strips. Draw a straight line in the middle of the paper. On the left-hand corner of the straight line, mark a point L. Draw a perpendicular LN on the straight line and produce it backward along LN1. Mark points P, Q and R on the line NL such that PL is equal to 2 cm, QL is equal to 4 cm and RL is equal to 6 cm. Fix common pins on the points P, Q and R in an upright position. These pins represent the location of 3 objects and a distance of 2 cm, 4 cm and 6 cm respectively. Now place the plane mirror along the straight line and hold it in a mirror stand. Shifting towards right hand side, locate the image P1 of the object pin P. Fix 2 common pins A and B such that these pins and the image P1 are in the same straight line. Fix 2 more pins C and D such that these pins and the image P1 are in the same straight line. Remove the mirror and then the pins A, B, C and D. Draw small circles around the pin points of A, B, C and D. A, B and CD represent reflected rays. Join AB and produce it backward till it meets the line LN1. Join CD and produce it backward till it joins line LN1. It is seen that AB and CD on producing back meet at the point P1. Thus, P1 is the position of the virtual image formed by the plane mirror when P acts as an object. Measure the distance P1L and record it. P1L is equal to 2 cm. Repeat the experiment 2 more times by taking pin Q and pin R as the object at distances 4 cm and 6 cm respectively. Measure the distance of image Q1 and R1 from the plane mirror and record it. Q1L is equal to 4 cm and R1L is equal to 6 cm. From the table, it is clear that distance of the object from the plane mirror is equal to distance of the image from the plane mirror. Thus, we conclude images are formed as far behind the plane mirror as the object is in front of it. To find focal length of a concave mirror by 1. Focusing a distant object on the screen. 2. Single pin method by removing parallax between the object pin and the image. Apparatus required: concave mirror of focal length between 10 cm to 20 cm, concave mirror stand, object pin with the stand, meter scale and wide screen. Procedure: 1. Determination of focal length by focusing distant object on the screen. Fix the concave mirror in the mirror stand in the vertical position. Face the mirror towards a distant tree. Place a white screen in front of the concave mirror. Move the white screen backward or forward till a well-defined inverted image of the tree is formed on the screen. Measure the distance between the white screen and the concave mirror with the help of meter scale. The distance so calculated is the focal length of concave mirror. Focal length of concave mirror is equal to 15 cm. 2. Determination of focal length by parallax method using a single pin. Mount the concave mirror in the mirror stand in the vertical position. Mount the object pin in its stand. Raise the object pin up or down such that its tip is in line with the pole of the concave mirror. Place the object pin in front of the concave mirror and look for its inverted image, keeping the line of sight in level with the tip of the pin. Move your line of sight slightly towards left and then towards right. You notice that image of the pin either moves slow or fast with respect to the object pin. In such a situation, there is a parallax between the object pin and its image. Move the object pin backward or forward till at some point the image does not appear to separate from the object pin. In such a situation, there is no parallax between the image and object pin. The parallax is removed only if the image is formed directly over the object. In such a situation, the object pin and its image are at the center of curvature of the concave mirror. Measure the distance between the object pin and the concave mirror. This distance is equal to the radius of curvature of concave mirror. Radius of curvature of the concave mirror R is equal to 30 cm. Therefore, focal length of the concave mirror F is equal to R upon 2 is equal to 30 upon 2 is equal to 15 cm. To draw inferences regarding current and resistance of an electric circuit with the help of electric bulbs when 1. The bulbs are connected in series and 2. The bulbs are connected in parallel. Apparatus required. 2 1.5 volts bulbs mounted in the bulb holders such that the terminals of the bulb holders are connected to insulated copper wires 10 cm long. Plug key, dry cell and sellotape. Procedure. Connect the bulb to a dry cell through a plug key with insulated copper wires. Hold the copper wires to the ends of the dry cell with sellotape. Insert the plug in the key. You noticed that bulb glows brightly. Remove the plug from plug key. Connect another bulb in series with the first bulb. Insert the plug key. You noticed that both the bulbs glow. However, they glow dimly as compared to the single bulb. Now remove one of the bulbs from its holder. It is observed that the second bulb stops glowing. Conclusions. In series circuit, the current flows only if all the elements of circuit are in electrical contact. In series circuit, the total resistance increases. This leads to the fall in the magnitude of the current. It is because of the fall in the magnitude of the current that bulbs in series glow dimly. Now, connect the bulbs in parallel circuit. Insert the plug key. You noticed that both the bulbs glow brightly. Remove one of the bulbs from its holder. You noticed that the second bulb continues glowing brightly. Conclusions. In parallel circuit, if one of the element is not in electrical contact, it does not function, but the rest of circuit functions normally. In parallel circuit, the total resistance decreases. This leads to the increase in the magnitude of the current from the cell. It is because of the decrease in total resistance of the bulbs, the current increases, and hence both the bulbs glow brightly.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
To plot magnetic field lines without any magnet nearby using small tracing compass. 2. To plot magnetic field lines around a magnet placed in the Earth's magnetic meridian such that north pole of the magnetic points towards geographic north. Apparatus required: wooden drawing board, 2 white sheets of paper, sellotape, tracing magnetic compass, and bar magnet. Procedure 1. For plotting Earth's magnetic field lines only. Fix the white sheet of paper on the drawing board and hold it in position by fixing sellotape at its corners. In the middle of the sheet, draw a straight line AB. In the middle of the straight line AB, place the tracing magnetic compass such that printed north-south on its base is aligned to the straight line AB. Now, turn the drawing board in the clockwise or anti-clockwise direction, such that the north pole of the tracing needle is aligned to the straight line AB. At this moment, the drawing board is aligned to the magnetic meridian of the Earth. Mark the boundary of the drawing board with a chalk. Mark the points D, F, H and J at one end of the paper. Place the tracing compass at point D in such a way that its south pole is aligned to the point D. Mark a point on the paper which is aligned to the north pole of tracing needle. Lift the tracing needle and place it in such a way that its south pole is aligned with the new point. Continue marking the direction of the north pole of tracing needle till you reach the other end of the paper. Join all the points marked. You noticed that all the points are on the same straight line CD. Thus, line CD represents magnetic line of force due to Earth. Repeat the experiment from the points F, B, H and J. It is seen that magnetic field due to the earth is in the form of parallel straight lines CD, EF, AB, GH and IJ. 2. For plotting magnetic field around a weak magnet placed in Earth's magnetic meridian. Fix the white sheet of paper on the drawing board and hold it in position by fixing sellotape at its corners. In the middle of the sheet, draw a straight line AB. In the middle of the straight line AB, place a tracing magnetic compass such that printed north-south on its base is aligned to the straight line AB. Now turn the drawing board in clockwise or anti-clockwise direction such that the north pole of the tracing needle is aligned to the straight line AB. At this moment, the drawing board is aligned to the magnetic meridian of the Earth. Mark the boundary of the drawing board with a piece of chalk. Now place the bar magnet in the middle of the line AB such that its north pole points towards the geographic north. Mark the boundary of the magnet. On either side of the boundary of the magnet, take 6 points. Start plotting magnetic lines of force with respect to each point and join them by smooth curves. Remove the magnet and draw CD, the right bisector of the length of the magnet. Replace the magnet in its original position. Now place the magnetic compass on the line CD such that it is on the left-hand side of the magnet. Carefully observe the direction of the magnetic needle. Move the needle backwards towards C and gently tap it. The point where the magnetic needle suddenly changes its direction or starts pointing in any direction is the neutral point. Similarly, locate neutral point towards D, the region N, and N on either side of the line CD are neutral points. The region X1 have weakest magnetic intensity. The regions around the poles of the bar magnet have strongest magnetic intensity. 1. To determine the least count of vernier calipers. 2. To measure the length and diameter of a small cylinder. Apparatus required: vernier calipers, wooden cylinder. Procedure: to calculate the least count of vernier calipers. A. Determination of pitch. Have a close look at the main scale of the vernier calipers. Count the number of divisions in 1 centimeter. Number of divisions on main scale in 1 centimeter is equal to 10. Therefore, pitch of vernier calipers is equal to 1 upon number of divisions on main scale centimeter, which is equal to 1 upon 10 centimeter, which is equal to 0.1 centimeter. B. Determination of the least count. Count the number of divisions on the vernier scale. Number of divisions on vernier scale is equal to 10. Therefore, least count of vernier calipers is equal to pitch upon number of divisions on vernier scale centimeter, which is equal to 0.1 upon 10 centimeter, which is equal to 0.01 centimeter. 2. To measure the length and diameter of a small cylinder. A. Determination of the length of cylinder. Hold the cylinder lengthwise in the external jaws of the calipers tightly. Determine the position of the zero of vernier scale on the main scale and hence record the number of divisions on the main scale before 0. Look for the vernier scale division which coincides with any of the main scale division. Record the number of vernier scale divisions which coincide with the main scale. Repeat the experiment 3 times more by turning the cylinder about its horizontal axis. Calculate the length of the cylinder in each case by applying the formula. Length of the cylinder is equal to main scale divisions into pitch plus vernier scale divisions into least count. Calculate the average length of the cylinder from the tabular data. Therefore, average length is equal to L1 plus L2 plus L3 plus L4 upon 4 is equal to 2.47 plus 2.45 plus 2.47 plus 2.45 upon 4 is equal to 9.84 upon 4 is equal to 2.46 centimeters. B. Determination of the diameter of cylinder. Hold the cylinder vertically in the external jaws of the calipers tightly such that the external jaws are at right angles to the curved surface of the cylinder. Determine the position of the zero of the vernier scale on the main scale and hence record the number of divisions on the main scale before 0. Look for the vernier scale division which coincides with any of the main scale division. Record the number of vernier scale divisions which coincide with the main scale. Repeat the experiment 3 times more by turning the cylinder about its vertical axis. Calculate the diameter of the cylinder in each case by applying the formula. Diameter of the cylinder is equal to main scale divisions into pitch plus vernier scale divisions into least count. Calculate the average diameter of the cylinder from the tabular data. Therefore, average diameter is equal to D1 plus D2 plus D3 plus D4 upon 4 is equal to 1.75 plus 1.73 plus 1.74 plus 1.74 upon 4 centimeter is equal to 6.96 upon 4 centimeter, and this is equal to 1.74 centimeter. 1. Determination of zero error, zero correction, pitch and least count of a given screw gauge. 2. Determination of the mean radius of a given wire by taking 3 sets of readings in perpendicular directions. Apparatus required: screw gauge, copper wire of length about 4 cm and diameter between 1 mm and 2 mm. Procedure. Note: if the screw gauge with zero error is not available, the zero error can be created in it by pasting 2 or 3 small strips of sellotape on its fixed jaw, that is, the stud. 1. Determination of the pitch of screw gauge. Close the jaws of the screw gauge by turning the circular scale screw till the ratchet becomes free. Turn the screw in the anti-clockwise direction such that it completes 5 rotations. Record the distance moved by the screw on the main scale. Distance moved by the screw on the main scale is equal to 0.5 centimeters. Calculate the pitch of the screw gauge by the formula. Pitch of the screw gauge is equal to distance moved by the screw on the main scale upon number of rotations of the screw is equal to 0.5 upon 5, and this is equal to 0.1 centimeter. 2. Determination of least count of screw gauge. Record the number of divisions on the circular scale. Number of divisions on the circular scale is equal to 100. Calculate the least count of the screw gauge by the formula. Least count of the screw gauge is equal to pitch upon number of circular scale divisions, which is equal to 0.1 centimeter upon 100 is equal to 0.001 centimeter. 3. Determination of zero error. Close the jaws of the screw gauge by turning the circular scale screw till the ratchet becomes free. Locate the position of the zero mark of the circular scale with respect to baseline on the main scale. If the zero mark of the circular scale is below the baseline of the main scale, then the zero error is positive. Find the marking of the circular scale which coincides with the baseline of the main scale. The marking on the circular scale is 25. Therefore, positive error is equal to marking on the circular scale into least count is equal to 25 into 0.001 centimeter is equal to 0.025 centimeter. 4. Determination of correction due to zero error. The error is positive, then correction is equal to minus positive error is equal to minus 0.025 centimeter is equal to minus 0.025 centimeter. 5. Determination of radius of thin wire. Pitch of the screw gauge is equal to 0.1 centimeter. Least count of the screw gauge is equal to 0.001 centimeter. Zero error is equal to Positive error is equal to 0.025 centimeter. Correction is equal to minus positive error is equal to minus 0.025 centimeter. Place the given wire in between stud A and movable screw B in vertical plane and turn the ratchet in the clockwise direction till the ratchet becomes free. Note the number of divisions through which the screw moves on the main scale from the left of the 0 mark on the circular scale. Note the circular scale reading which coincides with the baseline of the main scale. Calculate the observed diameter of the wire by the formula. Observed diameter is equal to number of divisions on main scale into pitch plus number of divisions on the circular scale into least count, which is equal to 2 into 0.1 centimeter plus 76 into 0.001 centimeter is equal to 0.276 centimeter. Calculate the corrected diameter by the formula. Corrected diameter is equal to observed diameter minus 0 correction. Repeat the experiment 2 more times and hence calculate the corrected diameter. Find the mean diameter. Mean diameter is equal to d1 plus d2 plus d3 upon 3 is equal to 0.251 plus 0.253 plus 0.252 upon 3 centimeter is equal to 0.756 upon 3 centimeter is equal to 0.252 centimeter. Find the mean radius by the formula. Mean radius is equal to mean diameter upon 2, which is equal to 0.252 upon 2 centimeter is equal to 0.126 centimeter. 1. To find the density of a glass block or glass slab by calculating its volume and mass in CGS and SI systems. 2. To establish relation between the density in CGS system and density in SI system. Apparatus required: 15 cm measuring scale, glass block, physical balance. Procedure: measurement of length. Place the glass block flat on the table. Place the measuring scale on the top of the glass block such that it is in line with the edge of the glass block and its zero end coincides with the edge of the glass block. The reading on the other edge of the glass block gives its length. Record the length. L1 is 10.9. Measure and record the length 2 more times from different places on glass block. Calculate the mean length. L is equal to L1 plus L2 plus L3 upon 3, which is equal to 10.9 plus 10.7 plus 10.8 upon 3 is equal to 32.4 upon 3 is equal to 10.8 centimeter. Measurement of breadth. Measure and record the breadth at least 3 times from different places of glass block. B1 is 4.9 centimeter, B2 is 4.7 centimeter and B3 is 4.7 centimeter. Calculate the mean breadth. B is equal to B1 plus B2 plus B3 upon 3 is equal to 4.9 plus 4.7 plus 4.7 upon 3 is equal to 14.3 upon 3 is equal to 4.8 centimeter. Measurement of thickness. Measure and record the thickness at least 3 times from different places of glass block. H1 is 2.6 centimeter, H2 is 2.5 centimeter and H3 is 2.5 centimeter. Calculate the mean thickness. H is equal to H1 plus H2 plus H3 upon 3 is equal to 2.6 plus 2.5 plus 2.5 upon 3 is equal to 7.6 upon 3, which is equal to 2.5 centimeter. Calculation of volume. Multiply the mean length, mean breadth and the mean thickness of the glass block and hence calculate the volume correct to 1 decimal place. Volume of glass block is equal to length into breadth into thickness is equal to 10.8 centimeter into 4.8 centimeter into 2.5 centimeter, which is equal to 129.6 centimeter cube. Measurement of mass. Place the glass block in the left-hand side of a physical balance. Place standard weights in right-hand side pan till the pointer comes in center. Calculate and record the mass of the glass block. Mass of the glass block is equal to 332 grams. Observations and calculations. Density of glass block in CGS system is equal to mass of glass block in grams upon volume of glass block in centimeter cube is equal to 332 grams upon 129.6 centimeter cube is equal to 2.56 gram per centimeter cube, corrected to 2 decimal places. Density of glass block in SI system is equal to mass of glass block in kilograms upon volume of glass block in meter cube. Density of glass block in SI system is equal to mass of glass block in gram upon 1000 divided by volume of glass block in centimeter cube upon 10 lakh is equal to 332 upon 1000 kg divided by 129.6 upon 10 lakh meter cube is equal to 332 upon 1000 into 10 lakh upon 129.6 kilogram meter cube is equal to 2560 kilogram per meter cube. Relation between density in SI system and CGS system. Density in SI system in kilogram per meter cube upon density of CGS system in gram per centimeter cube is equal to 2560 upon 2.56 is equal to 1000. Therefore, density in SI system in kilogram per meter cube is equal to 1000 into density in CGS system in gram per centimeter cube. 1. To find the volume of a metal bob by using a measuring cylinder. 2. To find the volume of same metal bob by using vernier calipers. And 3. To comment on the accuracies of the above methods. Apparatus required. Measuring cylinder 50 ml, beaker containing tap water, vernier calipers, metal bob used for simple pendulum experiments, and fine cotton thread. Procedure. A. To find the volume of metal bob by using measuring cylinder. Pour about 15 to 20 cc of water in a clean measuring cylinder. Keeping the eye in line with the lowest point of water meniscus, read and record the initial volume of water. Initial volume of water is equal to 18 cc. Tie a fine cotton thread to the hook of the metal bob. Lower the metal bob gently into the cylinder containing water such that the bob is completely immersed in water, but not the hook. Read and record the new volume of water by keeping the line of sight in line with the lowest point of meniscus. Final volume of water is equal to 23 cc. Calculate the volume of the metal bob by subtracting the value of initial volume from the final volume. Volume of the metal bob is equal to 23 minus 18 is equal to 5 cc. Pour about 4 cc of more water in the measuring cylinder. Repeat the experiment as explained above so as to obtain 3 sets of readings. Initial volume of water is equal to 22 cc. Final volume of water is equal to 27 cc and volume of the metal bob is equal to 27 minus 22 is equal to 5 cc. Calculate the mean volume of the metal bob from the tabular data. Therefore, mean volume of the metal bob is equal to 5 plus 5 plus 5 upon 3 cc is equal to 15 upon 3 cc, which is equal to 5 cc. B. To find the volume of metal bob by using vernier calipers. 1. Calculation of pitch. Count the number of divisions on the main scale of vernier calipers. Number of divisions in 1 centimeter of the main scale is equal to 10. Calculate the pitch of the vernier calipers by the formula pitch of vernier calipers is equal to 1 centimeter upon number of divisions in 1 centimeter is equal to 1 upon 10 centimeter is equal to 0.1 centimeter. 2. Calculation of least count. Number of vernier scale divisions is equal to 10. Calculate the least count of vernier calipers by the formula. Therefore, least count of the vernier calipers is equal to pitch upon number of vernier scale divisions is equal to 0.1 centimeter upon 10, which is equal to 0.01 centimeter. 3. Calculation of diameter of metal bob. Hold the metal bob in the external jaws of the vernier calipers. Record the number of divisions on the left of 0 of vernier on the main scale. Record the number of vernier scale divisions which coincide with any division of the main scale. Calculate diameter of the bob by the formula diameter is equal to main scale division into pitch plus vernier scale division into least count. Repeat the experiment 2 times more by holding the metal bob in external jaws from different positions. Calculate the diameter of the bob in each case. Calculate the mean diameter. Therefore, mean diameter D is equal to D1 plus D2 plus D3 upon 3 is equal to 2.05 plus 2.06 plus 2.08 upon 3 centimeter is equal to 6.19 upon 3 centimeter, which is equal to 2.06 centimeter. Calculate the mean radius by dividing diameter by 2. Therefore, mean radius R is equal to D upon 2 is equal to 2.06 upon 2 is equal to 1.03 centimeter, which is equal to 1.03 centimeter corrected to 2 decimal places. Calculate the volume of metal by the formula. Therefore, volume of the metal bob is equal to 4 by 3 pi r cube is equal to 4 by 3 into 22 by 7 into 1.03 the whole cube cc is equal to 88 by 21 into 1.09 cc is equal to 4.56 cc. Comments on the accuracy of the methods. In case of measuring cylinder, the accuracy of measurement is plus minus 1 cc, as we cannot measure volume accurately if it is less than 1 cc. In case of vernier calipers, the accuracy is up to 0.01 cc, as we can measure diameter accurately up to 0.01 centimeter. Thus, in way of volume measured by a vernier calipers is 100 times accurate as compared to the volume measured by the measuring cylinder. 1. To find relationship between the effective length of a simple pendulum and its time period. 2. To plot a graph between the effective length L and the square of time period t square, and hence find slope of graph. 3. To calculate acceleration due to gravity using the formula 4 pi square into slope. Apparatus required. Brass bob suspended from a light and preferably unspun cotton thread at least 120 cm in length. Iron stand with a clamp. Cork cut vertically into 2 halves. Meter scale. Vernier calipers. and a stopwatch. Procedure. With the help of vernier calipers, find the diameter of the brass bob, correct to nearest millimeter using main scale only. Record the diameter. Calculate and record radius r of the brass bob by dividing the diameter by 2. Diameter of the brass bob D is equal to 20 mm is equal to 2 cm. Therefore, radius of the brass bob R is equal to D upon 2 cm is equal to 2 upon 2 cm is equal to 1 cm. Now, set up the pendulum such as that length L1 is equal to 80 minus R centimeter. This will make effective length equal to 80 centimeter. Adjust the clamp of the iron stand so that brass bob is approximately 2 centimeter from the floor. Stretch the pendulum to one side such that it makes an angle of approximately 5 degrees with the vertical. Release the pendulum and at the same time start the stopwatch. Find the time period for 20 complete oscillations of pendulum and record. Time for 20 oscillations is 36 seconds. Repeat the experiment 3 times more such that effective length L is 90 cm, 100 cm and 110 cm. Time period is 38, 40 and 42 respectively. Find the time period T, that is, time for one oscillation and record it for each set of readings. Calculate time squared, correct to 1 decimal place in each case and record it in the table. Plot a graph between L versus T squared, taking L on y-axis and T square on x-axis. Scale on the x-axis is to 5 small squares is equal to 0.2 second square. Scale on the y-axis is to 1 small square is equal to 1 centimeter. Calculate the slope of the graph, that is, intercepts on y-axis divided by intercepts on x-axis. Calculate the acceleration due to gravity by the formula g is equal to 4 pi square into slope of the graph. Slope of the graph. Slope of the graph is equal to intercepts on y-axis upon intercepts on x-axis is equal to 110 minus 80 centimeter upon 4.4 minus 3.2 second square is equal to 30 centimeter upon 1.2 second square, which is equal to 25 centimeter per second square. Calculation of acceleration due to gravity. Acceleration due to gravity is equal to 4 pi square into slope of graph is equal to 4 into 22 into 22 upon 7 into 7 into 25 centimeter upon second square is equal to 1936 upon 49 into 25 centimeter upon second square is equal to 987.7 centimeter per second square. To verify the Archimedes principle, apparatus required: sensitive spring balance, 0 to 100 gram force, metal ball with a hook about 50 gram force, cotton thread, overflows jar, measuring cylinder 0 to 100 milliliter, wooden block, beaker containing tap water. Procedure: take a clean metal ball with a hook and tie it to a fine thread. On the other end of the cotton thread, make a loop. Check the spring balance for the zero error and record it. Zero error in the spring balance is equal to 4 gram force. Suspend the metal ball from the hook of the spring balance. Measure and record its weight in air. Observed weight of the metal ball in air is equal to 48 gram force. Find the true weight of the metal ball in air by subtracting the zero error from the observed weight in air. Corrected weight of metal ball in air is equal to 48 minus 4 gram force is equal to 44 gram force. Place the overflow jar on the wooden block and slowly pour in it water till the water starts overflowing through the spout. At this moment, stop pouring more water. In a few moments, the water from the spout stops overflowing. In this situation, the water in the overflow jar is at the verge of overflowing. Place a clean and dry measuring cylinder under the spout of the overflow jar. Now gently lower the metal ball, which is suspended from the hook of the spring balance, into the water in the overflow jar. You notice that as the metal ball goes inside the water, the spring balance registers less weight. Also, at the same time, the water overflows through the spout and collects in the measuring cylinder. Measure and record the weight of the metal ball when it is completely immersed in the water. Also, measure and record the volume of water in the measuring cylinder. Observed weight of the metal ball in water is equal to 30 gram force. Volume of water displaced by the solid is equal to 18 centimeter cube. Calculate the apparent loss of weight of metal ball in the water. Also calculate the weight of water displaced, knowing 1 centimeter cube of water is equal to 1 gram force. You find that the weight of water displaced by the immersed metal ball is equal to the apparent loss of weight of metal ball. Observations and calculations. Zero error in the spring balance is equal to 4 gram force. Observed weight of the metal ball in air is equal to 48 gram force. Therefore, corrected weight of metal ball in air is equal to 48 minus 4 gram force is equal to 44 gram force. Observed weight of metal ball in water is equal to 30 gram force. Therefore, corrected weight of metal ball in water is equal to 30 minus 4 gram force, which is equal to 26 gram force. Therefore, apparent loss of weight of metal ball in water is equal to 44 minus 26 gram force is equal to 18 gram force. Volume of water displaced by the solid is equal to 18 centimeter cube. Knowing 1 centimeter cube of water is equal to 1 gram force, weight of water displaced by the solid is equal to 18 gram force. Conclusions. It is clear that the weight of water displaced by metal ball is equal to the apparent loss of weight of metal ball in water. Thus, Archimedes' principle is verified.
Goyal brothers Prakash to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
1. To make test tube hydrometer using a test tube. 2. To determine RD of any two liquids. Apparatus required. Clean hard glass test tube about 15 cm long. Measuring cylinder of 500 cc about 20 to 25 cm long. Millimeter graph paper. Pair of scissors. Sellotape. Water. Lead shots, alcohol, and brine solution. Procedure. Take a 500 cc measuring cylinder and pour in it about 400 cc of water. Take a millimeter graph paper and cut a strip from it, which is 15 cm long, equal to the length of the test tube and 1 cm wide. Slip the graph paper strip into the test tube and hold it in position by a small strip of sellotape. Add about 20 lead shots in the test tube and try to float it in the cylinder filled with water. If the test tube floats in a tilted position, add few more lead shots till the test tube starts floating in an upright position. Add 4 lead shots so as to increase the stability of floating test tube. Read the length of test tube immersed in water in millimeters and record it. The length of test tube immersed in water, H water, is equal to 96 millimeter. Pour off water from the cylinder. Fill the cylinder with brine solution and float the test tube in it. Read the length of test tube immersed in brine solution in millimeters and record it. The length of test tube immersed in the brine solution, H brine, is equal to 80 millimeter. Pour off brine solution from the cylinder. Wash the cylinder with water and allow it to dry. Fill the cylinder with alcohol and float the test tube in it. Read the length of test tube immersed in alcohol in millimeters and record it. The length of test tube immersed in alcohol, H alcohol, is equal to 120 millimeter. Observations and calculations. Length of test tube immersed in water H water is equal to 96 mm, length of test tube immersed in brine solution H brine is equal to 80 mm, length of test tube immersed in alcohol H alcohol is equal to 120 mm. Therefore, relative density of brine solution is equal to H water upon H brine is equal to 96 mm upon 80 mm is equal to 1.2, and therefore relative density of alcohol is equal to H water upon H alcohol is equal to 96 mm upon 120 mm, which is equal to 0.8. To find relationship between Fahrenheit scale and Celsius scale of temperature. Apparatus required: Celsius thermometer, Fahrenheit thermometer, two 250 cc beakers, iron stand, glass stirrer, source of boiling hot water. Procedure: suspend Fahrenheit and Celsius thermometers side by side from the iron stand. Under the thermometers, place a 250 cc empty beaker. Adjust the clamp of the iron stand in such a way that the bulb of each thermometer is in the middle of the beaker. Collect boiling hot water in the second beaker from the source of boiling water such that 2/3 of the beaker is filled with boiling hot water. Pour the boiling hot water in the first beaker and wait for 1 minute or more. After 1 minute, when the temperature shown by Celsius thermometer is 80 degrees Celsius, read the corresponding temperatures from the Fahrenheit thermometer. Record the temperatures. Stir the water gently with the glass rod. When the temperature of the Celsius thermometer drops to 70 degrees Celsius, 60 degrees Celsius, 50 degrees Celsius, 40 degrees Celsius and 30 degrees Celsius, read and record the corresponding Fahrenheit temperatures. The temperatures are 158 degree Fahrenheit, 140 degree Fahrenheit, 122 degree Fahrenheit, 104 degree Fahrenheit and 86 degree Fahrenheit respectively. Plot a graph between the above temperatures, taking Celsius temperature on x-axis and Fahrenheit temperature on y-axis, starting both scales from 0. Scale on the x-axis is to 1 small square is equal to 2 degrees Celsius and scale on the y-axis is to 1 small square is equal to 4 degree Fahrenheit. Calculate the slope of the graph, that is, intercepts on y-axis divided by intercepts on x-axis. Record the intercept TF when TC is equal to 0. Slope of the graph is equal to delta y upon delta x is equal to 72 upon 40 is equal to 1.8. Temperature in Fahrenheit TF when temperature in Celsius Tc is equal to 0 is 32 degree Fahrenheit. To find a relationship between the angle of incidence and the angle of reflection using a plane mirror. Apparatus required: wooden drawing board, white sheet of paper, common pins, plane mirror with stand, geometrical instruments, and sellotape. Procedure: fix a white sheet of paper on the drawing board with the help of strips of sellotape. Mark a straight line in the middle of the white sheet. Mark a point O in the middle of the straight line and draw perpendicular ON with the help of a protractor. With the help of protractor, draw angle I is equal to DON is equal to 30 degree. Also draw angles D1ON, D2ON, D3ON and D4ON equal to 35 degree, 40 degree, 45 degree and 50 degree respectively. Now place the plane mirror along the line AB and hold it in a mirror stand. Fix two common pins P and Q on the line DO in an upright position such that the minimum distance between the pins is 3 cm. Look for the images of pins P and Q in the mirror and fix two more pins R and S such that the pins R and S and the images of the pins P and Q are in the same straight line. Remove the mirror and then the pins one by one. Draw small circles around the pin points so as to mark the position of the pins. Measure and record the angle of reflection, angle R. Angle of reflection, angle R, is 30 degree. Repeat the experiment by fixing the pins on line D10, D20, D30, D40 and in each case record the angle of reflection in tabular form. Angle of reflections are 36 degrees, 40 degrees, 44 degrees and 50 degrees respectively. From the observation table, it is clear that angle of incidence is equal to angle of reflection.
To verify the laws of reflection of sound. Apparatus required. 2 aluminium tubes highly polished from inside with a length of 25 cm and diameter 2 cm. 2 toothpicks. Sellotape. Full drawing sheet. Geometry box. Tuning fork. Rubber pad. Plasticine. Metal plate. Procedure. Spread the full drawing sheet on a table and hold it in place with the help of sellotape strips. In the middle of the drawing sheet, draw a straight line and on it mark point B. At point B, draw a perpendicular. Place the highly polished metal plate along the line MM1 in vertical position and hold it in place with plasticine. Take each of the metallic tubes, highly polished from inside and on the inner ends. Fix a toothpick with the help of sellotape. Place one metallic tube on the left-hand side of the normal such that toothpick A is in line with point B and makes an approximate angle of 30 degrees to 40 degrees. Place the second metallic tube on the right-hand side of the normal such that toothpick C is in line with point B. Ask a classmate to strike a tuning fork with rubber pad and hold it near the tube on the left-hand side. Do not touch it. Put your ear close to the tube on the right-hand side. Move the tube sideways till you clearly hear the sound of the tuning fork. For hearing sound, there should be a complete silence in the laboratory. Mark lines with the help of pencil along the toothpicks. Remove the tubes. Extend the lines in the form of dotted lines. Measure the angle of incidence on the left-hand side of the normal and the angle of reflection on the right-hand side of the normal. Repeat the experiment 3 more times by changing the angle of incidence. Record the angle of reflection in each case. Result. Within experimental limits, the angle of incidence is equal to the angle of reflection. As the incident sound wave, the normal and the reflected sound wave lie in the plane of drawing paper. Therefore, they lie in the same plane. To determine the density of a solid that is denser than water by using spring balance and measuring cylinder. Apparatus required. Glass stopper. Fine cotton thread. Sensitive spring balance 0 to 100 gram force. 100 cc measuring cylinder. Beaker containing water. Procedure. Take a clean glass stopper and tie it to a fine thread. On the other end of the cotton thread, make a loop. Check the spring balance for zero error and record it. Zero error in the spring balance equals 3 gram force. Suspend the glass stopper from the hook of the spring balance. Measure and record its weight. Observed weight of glass stopper equals 38 gram force. Now pour about 40 cc of water in the measuring cylinder. Measure and record the initial volume of water by keeping line of sight parallel to lowest point of concave meniscus. Initial volume of water in measuring cylinder equals 38 cc. Remove the glass stopper from the hook of the spring balance. Slip the glass stopper gently in the measuring cylinder containing water such that no air bubbles stick to the glass stopper. The level of water rises up in the measuring cylinder. Measure and record the final volume of water by keeping line of sight parallel to the lowest point of concave meniscus. Final volume of water in measuring cylinder equals 52 cc. Observations and calculations. Zero error in the spring balance equals 3 gram force. Observed weight of glass stopper equals 38 gram force. Therefore, corrected weight of glass stopper equals 38 gram force minus 3 gram force equals 35 gram force. Therefore, corrected mass of glass stopper equals 35 gram. Initial volume of water in measuring cylinder equals 38 cc. final volume of water in measuring cylinder equals 52 cc. Therefore, volume of glass stopper equals volume of water displaced equals final volume minus initial volume equals 52 cc minus 38 cc equals 14 cc. Therefore, density of glass stopper equals mass upon volume equals 35 grams upon 14 cc equals 2.5 gram per centimeter cube. Result: the density of glass stopper is 2.5 gram per centimeter cube. To establish the relation between the loss in weight of a solid when fully immersed in 1. Tap water, 2. Strongly salty water with weight of water displaced by it by taking at least 2 different solids. Apparatus required: spring balance 0 to 100 gram force, glass stopper about 50 grams, brass weight 50 gram, thin cotton thread, overflow jar, wooden block, pre-weighed beaker 37 gram force, 250 cc beaker containing tap water, 250 cc beaker containing strongly salty water, common compression balance. Procedure: take a clean glass stopper and tie it to a fine thread. Make a loop on the other end of cotton thread. Check the spring balance for zero error and record it. Zero error in the spring balance equals 4 gram force. Suspend the glass stopper from the hook of the spring balance. Read and record its weight in air. Observed weight of glass stopper in air equals 48 gram force. Place the overflow jar on the wooden block and slowly pour in it tap water till the water just starts overflowing through its spout. At this moment, stop pouring the tap water. In a few moments, the water from spout stops overflowing. In this situation, the water in the overflow jar is at the verge of overflowing. Place the clean and dry pre-weighed beaker under the spout of the overflow jar. Weight of beaker equals 37 gram force. Now, gently lower the glass stopper into the water in the overflow jar till it gets completely immersed. It is noticed that as the glass stopper goes under water, the spring balance registers less weight. Also, at the same time, the water overflows through spout and collects in the measuring pre-weighed beaker. Read and record the weight of glass stopper when fully immersed under water. Observed weight of glass stopper in water equals 30 gram force. Weigh the pre-weighed beaker along with displaced water on the common compression balance. Weight of pre-weighed beaker plus displaced water equals 55 gram force. Observation and calculation. Zero error in spring balance equals 4 gram force. Observed weight of the glass stopper in air equals 48 gram force. Corrected weight of glass stopper in air equals observed weight minus zero error equals 48 gram force minus 4 gram force equals 44 gram force. Weight of pre-weighed beaker equals 37 gram force. Observed weight of glass stopper in water equals 30 gram force. Corrected weight of glass stopper in water equals observed weight minus zero error. Equals 30 gram force minus 4 gram force equals 26 gram force. Therefore, apparent loss of weight of glass stopper in water equals corrected weight in air minus corrected weight in water equals 44 gram force minus 26 gram force equals 18 gram force. Weight of pre-weighed beaker plus displaced water equals 55 gram force. Therefore, weight of water displaced by glass stopper equals 55 gram force minus 37 gram force equals 18 gram force. It is noticed that loss of weight of glass stopper in water equals weight of water displaced by the glass stopper. Repeat the above experiment by immersing the glass stopper in the strongly salty water and brass weight in tap water and strongly salty water. You will notice that loss of weight of glass stopper in salty water equals weight of salty water displaced by the glass stopper. Loss of weight of brass weight in water equals weight of water displaced by the brass weight. Loss of weight of brass weight in salty water equals weight of salty water displaced by brass weight. Conclusion. It is clear that weight of water displaced by the glass stopper or brass weight is equal to apparent loss of weight of glass stopper or brass weight in water. This, in a way, verifies Archimedes' principle.
To observe and compare pressure exerted by solid iron cuboid on sand while resting on its three different faces, and to calculate the pressure exerted in three different cases. Apparatus required. A solid cuboid of iron of sides 1 cm into 2 cm into 3 cm, a rectangular wooden frame of sides 10 cm into 10 cm into 3 cm, a spring balance, two 200 gram force weights, wet sand, a small measuring scale. Procedure. Spread paper on the table and place the rectangular wooden frame of size 10 cm into 10 cm into 3 cm over it. Pour wet sand in the frame till 3 cm of sand is filled in the frame. Spread the sand evenly with the help of measuring scale so that a smooth and horizontal surface of it is formed. Find the weight of the solid cuboid by tying it to the hook of a spring balance with the help of cotton thread. Record the weight. Place the solid cuboid gently on the sand without any jerk, such that its surface area of 3 cm into 2 cm is in contact with sand. Place 200 gram force weight gently on the cuboid without any jerk. You will notice that the cuboid sinks slightly in the sand. This is on account of pressure exerted by the cuboid. Remove gently 1. 200 gram force weight 2. Cuboid. Notice the depression created and measure it with measuring scale. Smoothen the surface of sand and again place solid cuboid on it without jerk, such that its surface area of 3 cm into 2 cm is in contact with sand. Place 200 gram force weights gently on the cuboid without any jerk. You will notice that the solid cuboid sinks more as compared to step 5. Remove gently 1. 200 gram force weights 2. Cuboid. Notice the depression created and measure it with measuring scale. Repeat the experiment when 1. Surface area of 2 cm into 1 cm is in contact with sand. 2. Surface area of 3 cm into 1 cm is in contact with sand, and follow the step 5 to 9. Observations and calculations. Zero error in the spring balance is equal to 2
gram force.
Observed weight of the iron cuboid is equal to 42
gram force.
Corrected weight of the iron cuboid is equal to 42 minus 2
gram force
is equal to 40
gram force.
Total thrust when 200
gram force
weight is used is equal to 200
gram force
plus 40
gram force
is equal to 240 into 9.8 divided by 1000 is equal to 2.352
Newton.
Total thrust when 400
gram force
weight is used is equal to 400
gram force
plus 40
gram force
is equal to 440 into 9.8 divided by 1000 is equal to 4.312
Newton.
Surface area of 3 cm into 2 cm is equal to 6 cm square is equal to 6 into 10 raised to the power minus 4
meter square.
Surface area of 2 cm into 1 cm is equal to 2 cm square is equal to 2 into 10 raised to the power minus 4
meter square.
Surface area of 3 cm into 1 cm is equal to 3 cm square is equal to 3 into 10 raised to the power minus 4
meter square.
Contact surface area, thrust, pressure is equal to force upon area. 6 into 10 raised to the power minus 4
meter square.
2.352
Newton.
2.352
Newton
divided by 6 into 10 raised to the power minus 4
meter square
is equal to 0.392 into 10 raised to the power 4
Newton per meter square
is equal to 3920
Pascal.
4.312
Newton.
4.312
Newton
divided by 6 into 10 raised to the power minus 4
meter square
is equal to 0.7187 into 10 raised to the power 4
Newton per meter square
is equal to 7187
Pascal.
2 into 10 raised to the power minus 4
meter square.
2.352
Newton.
2.352
Newton
divided by 2 into 10 raised to the power minus 4
meter square
is equal to 1.176 into 10 raised to the power 4
Newton per meter square
is equal to 11760
Pascal.
4.312
Newton.
4.312
Newton
divided by 2 into 10 raised to the power minus 4 into
meter square
is equal to 2.156 into 10 raised to the power 4
Newton per meter square
is equal to 21560
Pascal.
3 into 10 raised to the power minus 4
meter square.
2.352
Newton.
2.352
Newton
divided by 3 into 10 raised to the power minus 4
meter square
is equal to 0.784 into 10 raised to the power 4
Newton per meter square
is equal to 7840
Pascal.
4.312
Newton.
4.312
Newton
divided by 3 into 10 raised to the power minus 4 into
meter square
is equal to 1.437 into 10 raised to the power 4
Newton per meter square
is equal to 14370
Pascal.
Conclusions. The pressure exerted by a solid increases with the thrust or force. The pressure exerted by a solid increases with the decrease in area of contact. Precautions. The sand should not be filled in wooden frame very tightly. The sand should be wet but not dripping water. Take accurate measurements of dimensions of cuboid before finding the surface area. Do not place the cuboid on sand with a
To determine the velocity of a pulse propagated through a stretched string or slinky. Apparatus required. Flat wire coiled spring or slinky of copper about 10 cm long and 7.5 cm in diameter. Meter rod. Stopwatch. Small wooden board. Procedure. Note: this experiment needs at least 2 students. The experiment should be conducted in the corridors of school with smooth floor or on smooth tabletop, which is not less than 6 meters. Mark a line on the floor. From this line, measure a distance of 6 meters accurately with the help of meter rod and mark another line, PQ, on the floor. Let one of the students, say S1, hold the slinky at point A. Let the other student, say S2, stretch the slinky to the point B. At the point A, let student S1 place a wooden block parallel to the end of the slinky. This wooden block acts as a stopper. Let the student S1 pull the string or slinky towards position C, which is 10 cm from A, and then give it a sharp push towards A, such that the motion of his hand stops at A because of wooden block. A pulse is produced in the slinky, which travels towards B. It is then reflected towards A and again towards B. Practice it 5 to 10 times till you are sure that you can generate a pulse and see it moving forward and backward. Now you are in a position to carry out the experiment. The student S2 will hold the stopwatch in his hand. When the student S1 generates a pulse, the student S2 will watch the pulse travel towards him. When the pulse reaches at B, the student S2 will start the stopwatch. This pulse on reflection will move towards point A and again towards point B. As soon as the pulse again reaches B, the student S2 will stop the stopwatch and will record the time for the pulse to travel from B to A and then back to B. The experiment is repeated 2 more times. The velocity of pulse is calculated by the formula. Velocity of pulse equals total distance travelled by pulse upon total time taken. Observation and calculation. Therefore, average velocity of pulse equals 4.3 plus 4.1 plus 4.4 meter per second upon 3 equals 4.3 meter per second. Result: velocity of pulse equals 4.3 meter per second. Note: for the same slinky, the velocity of pulse will increase if it is stretched more and vice versa.
To establish relationship between weight of a rectangular wooden block lying on a horizontal table and the minimum force required to just move it using a spring balance. Apparatus required. A spring balance 0 to 250 grams. A rectangular wooden block less than 50 grams with smooth surfaces and provided with hook. A glass plate rectangular of 25 cm by 25 cm. 4 50-gram weights from the set of slotted weights. A spirit level. Procedure. Place the glass plate along the edge of laboratory table. By placing the spirit level in the middle of glass plate, check that its surface is horizontal. In case surface is not horizontal, insert pieces of paper under the glass plate so that it is horizontal. Check the spring balance and record the zero error, if any. Zero error of spring balance is equal to 2.5 gram force. Suspend the wooden block from the hook of the spring balance. Record the weight of the wooden block. Weight of the wooden block is equal to 42.5 gram force. This weight is equivalent to normal reaction of the wooden block. Place the wooden block on the one edge of glass plate. Fix the hook of spring balance in the hook of wooden block. Gently pull the spring balance towards the right side and at the same time gently tap the glass plate. Gently go on increasing the pull till the wooden block just starts sliding. Read and record the force applied on the spring balance. Force applied on the spring balance is equal to 22.5 gram force. This force is equal to the linking force of friction. Now place 50 gram force weights on the wooden block. Weight of the wooden block plus 50 gram force of weight is equal to 92.5 gram force. Read as well as record limiting force of friction. Observed limiting friction is equal to 47.5 gram force. Repeat the experiment with 100 gram force, 150 gram force and 200 gram force weight. In each case, read and record limiting force of friction. Observations and calculations. Zero error of spring balance is equal to 2.5 gram force. Result. Force of limiting friction is directly proportional to normal reaction. The ratio between the limiting force of friction and the normal reaction is a constant quantity. Thus, force of limiting friction is directly proportional to the normal reaction. From this statement, it implies that with the increase in normal reaction, the force of friction increases.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores. Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
To look at plant cells. Materials required: onion bulb, knife, watch glass, iodine solution, dropper, glass slide, cover slip, needle, brush, forceps, microscope. Procedure: take an onion bulb and prepare a peel from the fleshy white layers of the bulb. Place a few pieces of peel in watch glass containing water. Put a drop of iodine in watch glass. After a few seconds, put a drop of water on a glass slide and place a piece of peel on it. Now, cover it with a cover slip with the help of a needle. Observe it under the microscope. Observation: there are a large number of cells with distinct cell walls. A largely stained nucleus is present in the periphery of cytoplasm. A prominent vacuole is present in the center of each cell. To look at animal cells. Materials required: cotton bud, glass slide, dropper, water, methylene blue solution, cover slip, needle, microscope. Procedure: take a clean glass slide and put a drop of water on it. Now, open your mouth and slightly scrap the inner part of your cheek with a clean cotton bud. Put the scraping on the slide in the drop of water. Add a drop of methylene blue solution. Place a cover slip on it and observe it under a microscope. Observation: a large number of flat cells with irregular boundaries are seen. Each cell has a thin cell membrane. A distinct deeply stained nucleus is seen. No cell wall is present in animal cells. To demonstrate diffusion. Materials required: beaker, water, potassium permanganate crystals, forceps. Procedure: take a beaker and fill the beaker more than half with distilled water. Place a small crystal of potassium permanganate at the bottom of the beaker and observe. Observation: the crystal starts dissolving immediately and color the water slowly. After the whole of the crystal is dissolved, the water gets uniformly colored.
Inference and conclusion. The experiment demonstrates that when there is no intervening partition, most molecules mix or diffuse into each other till they thoroughly make homogeneous mixture. Here, it shows the diffusion of solid into the liquid medium. In living processes, this phenomena of diffusion holds great importance for the movement of solutes. It is a passive process without involvement of metabolic energy. To demonstrate osmosis. Materials required: 2 thistle funnels, 2 stands, beaker half filled with water, goat's urinary bladders, sugar solution, thread. Procedure. Take a thistle funnel A and cover its mouth with a goat's urinary bladder. It acts as semi-permeable membrane. Invert the thistle funnel and fill it with concentrated sugar solution. Then insert the inverted thistle funnel in a beaker A containing water and mark the level of sugar solution in the thistle funnel. For control, take another thistle funnel B covered with a piece of urinary bladder, semi-permeable membrane. Invert this thistle funnel and fill it with plain water. Then insert the inverted thistle funnel in another beaker B containing some amount of water. Mark the level of plain water in the thistle funnel B. After a few hours. Observation. The level of water in the thistle funnel A increases. The level of water in thistle funnel B remains unchanged. If the water in the beaker A is tasted, it is found to contain no sugar. Inference. We can draw the following conclusions. Some water from the beaker A has passed through the goat's urinary bladder to sugar solution. Sugar from thistle funnel A has not come out in beaker, as the water in the beaker is not sweet. Urinary bladder A acts as a semi-permeable membrane. It allows water molecules to pass through, but not the sugar molecules. The level in the thistle funnel B does not rise because the concentration of water inside the thistle funnel B and beaker B is same.
To demonstrate osmosis using potato osmoscope. Materials required: potato tuber, beaker half filled with water, pin, knife, and sugar solution. Procedure. Take a large size potato. Peel off its skin and make its base flat. Make a hollow cavity in the center. Put some sugar solution and mark the level by pin. Place this osmoscope in a beaker half filled with water. Leave the apparatus undisturbed for 2 to 3 hours. After 2 to 3 hours. Observation. The level of sugar solution in the cavity of potato rises. Inference. The experiment shows the phenomenon of osmosis. The thin layer of cells in the cavity of potato tuber functions as a semi-permeable membrane. So the water molecules moved from their higher concentration to their lower concentration, that is, in sugar solution. To demonstrate exosmosis and endosmosis. Materials required. Petri dishes, some raisins, fresh grapes, concentrated sugar solution, water. Procedure. Take 2 Petri dishes A and B. Put some raisins in Petri dish A containing water. Keep some fresh grapes in Petri dish B containing concentrated sugar solution. Leave both the Petri dishes for a few hours. After a few hours. Observation. In Petri dish A, the raisins have swollen. In Petri dish B, the grapes have shrunk. Inference. The raisins contained a concentrated sap and therefore water molecules from the Petri dish A moved in through the semi-permeable membrane of the raisins, endosmosis. Similarly, as the grapes were kept in concentrated sugar solution in Petri dish B, water moved out through the semi-permeable membrane of the grapes, exosmosis.
To demonstrate plasmolysis, materials required: Royo discolor leaf, forceps, concentrated sugar solution, slide, brush, watch glass, dropper, water. Procedure. Make an epidermal peel from the leaf with the help of forceps. Keep the epidermal peel in a watch glass containing water. Put a drop of concentrated sugar solution on a clean glass slide. Now transfer a piece of leaf peel from the watch glass to the sugar solution on the slide. Observe the cell contents under the microscope. Observation. The purple-colored contents inside the cells start pulling away from the cell wall.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
To learn about the tissues responsible for growth in a plant. Materials required: glass jars filled with water, onion bulbs, scissors, ruler. Procedure: take 2 glass jars filled with water. Take 2 onion bulbs and place one each jar in such a manner that the base of the bulb is dipped in water. Observe on daily basis what happens to the bulbs in 2 jars. After 1 day. Observation: you observe the roots coming out of the bulbs. Now measure the length of roots on day 1 and 2. On 3rd day, cut the tips of the roots of onion bulb in jar A and leave jar B as such. Observe the growth of roots in both the jars for a few more days. Record your observation in a table. After 2 days, as a result, the length of roots in jar A is less than in jar B. After 3 days. This is because the growth of plants occurs only at certain specific regions, where the dividing tissue, called the meristematic tissue, is present. When the tips of the roots in jar A are cut, this tissue is cut. Hence, the growth stops. The meristematic tissues are responsible for growth in a plant. After 4 days. Length of root in centimeter. Jar A, jar B. Day 1, 1 centimeter, 1.2 centimeter. Day 2, 1.5 centimeter, 1.7 centimeter. Day 3, 1.5 centimeter, 2.2 centimeter. Day 4, 1.5 centimeter, 3.0 centimeter.
Nervous tissue. Nerve cells or neurons form the most important elements of the nervous tissue. Each neuron consists of 3 parts. The main body, called the cell body or cyton, the dendrons, and the axon. The dendrons are one or more short processes arising from the cyton. Dendrons branch further into many thin dendrites. The dendrites receive impulses. The axon is a single long cylindrical process arising from the cyton. The axon forms fine branches at its terminal end and takes impulses away from the cell body. Nerve cells are joined end to end, forming long nerve fibers. The nerve fibers conduct messages from one part of the body to the other. They also receive stimuli from the outside environment and send the message to the brain and spinal cord. In turn, impulses from the brain and spinal cord are carried to the various organs. To study fungi. Yeasts are single-celled organisms. Their name, Saccharomyces, means sugar fungi, and they are commonly found wherever sugar occurs. For thousands of years, yeast has been used to ferment the sugars in rice and barley to produce beer and the sugar in grapes to make wine. Yeast added to dough ferments the sugar in the dough to produce carbon dioxide. This makes the dough rise. Rhizopus nigricans is a common fungus found growing on dead and decaying organic matter, stale bread, decaying vegetables and fruits, jelly, pickles, and leather goods. The plant body consists of an interwoven mass of delicate, colorless, and thread-like hyphae. The ramifying network of loose hyphae is known as mycelium. Agaricus, commonly known as mushroom, is a common edible mushroom. It is found growing on damp, rotten logs of wood, trunks of trees, decaying organic matter, and in damp soil rich in humus. Agaricus or mushroom consists of two parts: subterranean part or mycelium and aerial part or sporophore. The mold Penicillium notatum produces a substance which can destroy bacteria. The substance called penicillin is an antibiotic used to fight diseases caused by bacteria.
To observe the different types of tissues in plant, materials required: young stem of a plant, dilute saffron in solution, glycerine, sharp razor, watch glass containing water, brush, dropper, slide, cover slip, a piece of potato tuber, microscope. Procedure: take a young stem of a plant. Cut the stem and potato tuber into very thin slices with the help of a sharp razor in a watch glass. Put a few drops of saffron in solution in watch glass. Put a drop of glycerine on a clean slide. Transfer a thin slice of stem on it and cover it with a cover slip. Observe it under microscope. Observation: different types of cells are seen in section. These different types of cells are arranged in a particular manner so that functions of protection, support, conduction, and secretion are suitably performed.
To study the leaf peel of royo. Materials required: freshly plucked royo leaf, petri dishes containing water, slide, cover slip, saffron in solution, dropper. procedure. Take a freshly plucked leaf of royu. Break it with pressure in such a manner that its peel comes out. Cut this peel and place it in a petri dish containing water. Put 2 drops of saffron in solution in petri dish to stain the peel. After 1 minute, transfer the peel in another petri dish containing water to wash it. Put a drop of glycerine on a clean slide. Transfer a piece of leaf peel on it. Cover the leaf peel with a cover slip and observe it under a microscope. Observation: cells of one kind that constitute the epidermis.
Epithelial tissue. Epithelium is a covering tissue which forms the outer protective covering all over the body and lines the inside of all cavities such as those of the mouth, throat, stomach, intestines, windpipe and lungs. The epithelial cells lie close together with little or no intercellular substance or matrix between them. There is no blood or lymph supply in epithelial tissue. Nerve supply is present. Epithelium may be one cell thick, that is, single-layered, simple epithelium, or it may be several cell thick, that is, many-layered, compound or stratified epithelium. Depending upon the shape and function of the constituent cells, epithelial tissues are of the following types. Squamous epithelium. The cells in the epithelium are extremely thin and flat and are arranged edge to edge, forming a delicate lining or covering. It forms the lining of cavities of blood vessels, lines the chambers of the heart, covers the skin and lining of the mouth and nose. This epithelial tissue is also called pavement epithelium. Columnar epithelium. This epithelium consists of cells which are much longer than broad, look like a column. It forms the lining of stomach and intestines, also found in salivary glands in the mouth, sweat glands and oil glands of the skin. Cuboidal epithelium. Cells are as long as broad and appear cube-like. A centrally located nucleus is present. It is found in some part of kidney tubules, duct of salivary glands, thyroid gland. Ciliated epithelium. This epithelium, usually consisting of cuboidal or columnar cells, has numerous thin, delicate, hair-like projections called cilia, arising from the outer free surface of the cells. It is found lining the windpipe, trachea, kidney tubules, and oviduct. Sensory epithelium. In some cases, the epithelial cells become modified to receive external stimuli. Such sensory cells have nerve endings so that they can perceive various stimuli found in the nasal passages, taste buds, retina of eyes. Stratified epithelium. This is a compound epithelium in which cells are arranged in many layers, one above the other. It is found in places where there is much wear and tear, such as epidermis of skin, lining of the mouth cavity, tongue, esophagus, and vagina.
Connective tissue proper. Connective tissue proper is of 4 types: areolar connective tissue, adipose connective tissue, tendons, and ligaments. Areolar connective tissue. Areolar connective tissue is the most widely distributed connective tissue in the body, having in the matrix irregular shaped cells and two kinds of fibers: white fibers made of collagen and yellow fibers made of elastin. Areolar connective tissue binds the skin with underlying parts. Adipose connective tissue. Adipose connective tissue occurs below the skin, around internal organs and yellow bone marrow. Cells are modified to store fat. Each cell consists of a large vacuole filled with fat which is surrounded by a small amount of cytoplasm containing a nucleus towards the periphery. Adipose connective tissue acts as a filling tissue, stores fat, and keeps the body warm. Tendons. Tendon is tough and non-elastic, made up of white fibers and connects muscle to bone. Ligaments. Though strong, ligaments are elastic, consisting of yellow fibers. They connect one bone to another bone.
Supportive connective tissue, skeletal tissue. Cartilage. Cartilage is a non-porous tissue. Cells of cartilage called chondroblast are embedded in the matrix in groups of 2, 4 or more in fluid-filled spaces called lacunae. Cartilage is usually covered by a tough fibrous membrane called perichondrium. Cartilage is found in nose tip, ear pinna, rings of windpipe, trachea, end of long bones, low end of ribs. In sharkfish, the whole skeleton is cartilaginous. Cartilage performs the function of providing support and flexibility in the vertebrate body. Bone. Bone is a very strong, rigid and porous tissue. The matrix is impregnated with phosphates and carbonates of calcium and magnesium. Blood vessels and nerves are present. The bone cells called osteocytes are present in concentric rings between the lamellae. On the outside, a bone is surrounded by a connective tissue called periosteum. Blood vessels and nerves are present in it. Bones protect the internal organs, support the body, and help in locomotion.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
Fluid connective tissue. Blood and lymph constitute the fluid connective tissue. Blood. Blood is a bright red colored fluid connective tissue. It consists of a straw-colored fluid called plasma, in which various kinds of cells or corpuscles are present. The blood cells are erythrocytes, the red blood cells or RBCs, leukocytes, white blood cells or WBCs, and blood platelets. The plasma makes up about 55% of the blood by volume, while blood cells make up 45% of the blood by volume. An adult human being contains about 6 liters of blood. Blood transports food materials, oxygen, carbon dioxide, and excretory products to the kidneys from where they are eliminated. It regulates temperature by distributing heat within the body. WBCs protect the body from diseases and help in wound healing. Platelets help in blood clotting. Lymph. Lymph is another fluid connective tissue consisting of plasma and mainly white blood cells. RBCs and platelets are absent. It is a fluid that surrounds the body cells. It mainly helps in the exchange of materials between blood and tissue fluids. To study fungi. Yeasts are single-celled organisms. Their name, Saccharomyces, means sugar fungi, and they are commonly found wherever sugar occurs. For thousands of years, yeast has been used to ferment the sugars in rice and barley to produce beer and the sugar in grapes to make wine. Yeast added to dough ferments the sugar in the dough to produce carbon dioxide. This makes the dough rise. Rhizopus nigricans is a common fungus found growing on dead and decaying organic matter, stale bread, decaying vegetables and fruits, jelly, pickles, and leather goods. The plant body consists of an interwoven mass of delicate, colorless, and thread-like hyphae. The ramifying network of loose hyphae is known as mycelium. Agaricus, commonly known as mushroom, is a common edible mushroom. It is found growing on damp, rotten logs of wood, trunks of trees, decaying organic matter, and in damp soil rich in humus. Agaricus or mushroom consists of two parts, subterranean part or mycelium and aerial part or sporophore. The mold Penicillium notatum produces a substance which can destroy bacteria. The substance called penicillin is an antibiotic used to fight diseases caused by bacteria. To study some algae. Spirogyra forms filaments of cells joined end to end. The filaments make a green tangled mat on the surface of ponds. Each cell is surrounded by a wall made of cellulase, which in turn is surrounded by a layer of slimy substance called mucilage. A ribbon-shaped chloroplast, which runs in a spiral manner, is present in each cell, giving Spirogyra its name. Eulothrix is found in the form of a slender filament composed of a single row of small rectangular cells. In attached filaments, the basal cell, by which filament is attached to the substratum, is elongated and narrow and is brown or white in color. It is known as holdfast. The cell wall is formed of cellulose and is followed by a layer of protoplasm having a central nucleus, a collar-shaped chloroplast, and a number of pyrenoids. A large vacuole filled with cell sap lies in the center of the cell. Ulva. Ulva is an edible sea lettuce. It is a marine water algae. Ulva species are common in the intertidal zones, which are found either as free-living or in attached form. Chara. Chara is plant-like in appearance in that it has a main stem with whorled leaf-like structures around it and a base.
To study sponges. The sponges are pore-bearer animals, that is, the body has many pores all over. The pores are called ostia. In addition, there is a single large opening called osculum at the top. The sponges have cellular organization. Cells are closely held together and there is no tissue or organ formation. Water, along with food, is drawn in through the ostia. Mouth and alimentary canal are absent. In addition to pores, the body has a characteristic canal system for circulation of water. Water carries food and oxygen with it. Water along with waste is moved out through the osculum. Most of the sponges are asymmetrical, some are radially asymmetrical. In sponges, skeleton is present. It consists of calcareous or siliceous spicules, needle-like structures, or proteinaceous spongin fibers. Examples: marine sponges, leucosolenia, Cycon, Spongia, Euplectilla, Eupspongia, bath sponge, freshwater sponge, Spongilla.
To study Hydra. Hydra is a freshwater animal belonging to the phylum Cnidaria. Hydra lives in ponds and water-filled ditches. Hydra is a multicellular animal which possess tissue-level organization with a distinct division of labor. In Hydra, body is radically symmetrical. The animal body can be divided into equal halves by any plane passing through the middle from top to bottom. The body has a single sac-like central cavity called coelenteron or the gastrovascular cavity with only one opening. In Hydra, the tentacles carry sting cells called cnidoblasts. Food enters and undigested remains leave through the same opening, the mouth anus. To examine a jellyfish. Aurelia or jellyfish are found in marine water. Aurelia has tissue-level organization with a distinct division of labor. In Aurelia, body is radially symmetrical. The animal body can be divided into equal halves by any plane passing through the middle for top to bottom. In Aurelia, the body has a single sac-like central cavity called coelenteron or gastrovascular cavity with only one opening. The body bears special stinging cells that are abundant in tentacles. To study tapeworm and roundworm. Tapeworm is a common flatworm parasite that lives in the intestines of vertebrates. The body is long and flat and made up of sections called proglottids. In tapeworm, body is bilateral symmetrical. Roundworms are either parasite or free-living. Most are free-living. They have narrow, elongated and cylindrical bodies. They are triploblastic, unsegmented animals with bilateral symmetry. Body cavity is not a true coelom. It is called pseudocoel or pseudocoelum. A complete alimentary canal with mouth and anus is present. The respiratory, circulatory and skeletal systems are absent.
Goyal brothers to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
To study earthworms. Earthworms occur in water or moist soils. Their body is composed of rings. In earthworm, first segmentation is known as peristomium, in which mouth is present. There is a prominent band called clitellum, which cover 3 segments. Earthworms are bilaterally symmetrical. Excretion occurs through coiled tubular structures called nephridia, singular nephridium. Blood vascular system consists of closed vessels. Blood is red due to the presence of the pigment hemoglobin.
To study mollusca. Mollusca are mostly aquatic, living in sea water. Some, however, occur in fresh water. They are soft, unsegmented, triploblastic, columnate animals. The soft body is usually supported by a hard shell exoskeleton of calcium carbonate. In mollusca, bilateral symmetry is present. The body is divided into an anterior head, a ventral muscular foot, and a dorsal visceral mass or hump. Over the hump is formed a fold of tissue called mantle or pallium. Mantle secretes the shell. Respiration occurs through gills called stenidia. Blood vascular system is of open type. It includes a dorsal heart arteries that opens into spaces and veins. Blood is usually blue due to the presence of blue pigment called hemocyanin.
To study a starfish. Starfish is exclusively marine animal. The body has a rough outer covering of spines or projections. Body is triploblastic, coelomate, and without segmentation. There is no head or tail, no left or right side. Radial symmetry is found in starfish. The digestive system is simple and complete. The mouth is on the lower surface and the anus is on the upper surface. Circulatory system is greatly reduced. There is no heart. Body cavity is modified into a water vascular system. Tube-like extensions called tube feet are present in this system. Tube feet help in locomotion and food collection. Excretory organs are absent and nervous system is primitive. It consists of a nerve ring and radial nerve cords. Brain is absent.
Transmission of diseases. Infectious diseases can be spread from an infected person to a healthy person by a number of methods: through air, water, sexual act, and through carriers. Diseases spread through air. A number of diseases causing microbes spread through air. This occurs through the little droplets thrown out when an infected person sneezes or coughs or spits. This is called droplet infection. After a few days, a healthy person standing nearby can inhale these droplets, causing infection in that person. Airborne diseases are more common in crowded areas as well as in poorly ventilated rooms. Diseases spreading through air: common cold, pneumonia, tuberculosis, diphtheria. Diseases spread through water. Some diseases can spread from one person to another when a sick person's stool gets into water. The stools may contain germs or eggs of worms. The people drinking the infected water thus gets the disease. It is therefore important to protect drinking water supplies from human and animal waste. After some time, diseases spreading through water: cholera, jaundice, diarrhea. Spread through physical contact. One of the ways of physical contact between two persons is a sexual act. Diseases like AIDS, syphilis, and gonorrhea are spread by sexual contact from one partner to another. Such diseases are not transmitted by casual physical contact like handshakes, hugs, sports like wrestling, or by any other ways in which we touch each other socially. Spread of AIDS. Besides sexual contact, AIDS virus can also spread through blood-to-blood contact, during blood transfusion, or by an infected needle or razor, and during pregnancy from an infected mother to her baby. Diseases spread through carriers. Many animals exist in the environment in which we live. These animals carry the disease-causing germs from an infected person to a healthy one. These animals thus act as carriers of diseases. Carriers of specific disease-causing germs are called vectors. Most common vectors are the mosquitoes. For example, malaria is caused by protozoan Plasmodium. However, this protozoan is carried from the infected person to the healthy person by a female Anopheles mosquito. This female mosquito requires a highly nutritious food in the form of blood in order to be able to lay eggs. When it bites an infected person, it sucks the blood along with the disease-causing germs. These germs get transmitted to a healthy person when the insect bites a healthy individual. Rabies in humans is caused by the bite of a rabid animal like a dog. The rabid animal is a vector of rabies virus. Diseases spread through bites of vectors: malaria, rabies.
To show the rates of cooling temperature in different situations. Materials required: water-filled beaker A, sand-filled beaker B, closed bottle containing a thermometer C. Thermometer. Procedure. Record the temperature of the sand, water and the bottle in the lab. Keep the 3 containers in the bright sunlight for about 2 to 3 hours. Now measure the temperature in all the 3 cases. Now keep the 3 containers in the shade for about 1 hour. Now measure the temperature in all the 3 cases. Beaker A, Beaker B. Bottle C. Initial stage 27 degrees Celsius, 27 degrees Celsius, 27 degrees Celsius. After keeping in sunlight 33 degrees Celsius, 38 degrees Celsius, 27 degrees Celsius. After keeping in shade 29 degrees Celsius, 27 degrees Celsius, 27 degrees Celsius. Conclusion. Land, that is sand, gets heated up faster than water. Land also loses heat faster than water. No temperature change occurs in vacuum condition.
To show movement of hot air. Materials required: 1 candle, 1 beaker, incense stick, matchstick. Procedure. Place a candle in a beaker and light it. Light an incense stick. Take the incense stick to the mouth of the beaker near the edge of the beaker. Keep a little above the candle. Keep it in other regions. Observation. All cases, fumes rise upwards. Conclusion. Hot air rises upwards. To show that 1. Oxygen is present in air and 2. Oxygen is required for burning. Materials required: glass trough, candle, water, glass tumbler. Procedure. Fix a candle in the middle of a trough. Pour water in the trough to a height of about 1.5 centimeter. Light the candle. You notice that the candle burns brightly. Now take a glass tumbler and invert it on the burning candle, such that the rim of the tumbler is immersed in water. You notice that the flame of candle flickers for a moment and then goes off. Leave the apparatus undisturbed for 10 minutes. After 10 minutes, you notice that the level of water rises up in the glass tumbler by 1/5 the volume of air in the tumbler. Harmful effects of air pollution. The harmful effects of some of the air pollutants are dizziness, headache, eye irritation, nasal irritation, coughing, sore throat. Air pollution affects the respiratory system of living beings and causes bronchitis, pneumonia, asthma, and lung cancer. Burning of fossil fuels like coal and petroleum releases oxides of nitrogen and sulfur. Not only is the inhalation of these gases dangerous, they also dissolve in rain to produce acid rain. The burning of fossil fuels also increases the amount of suspended particles in air. These suspended particles could be unburned carbon particles. Presence of these pollutants in air during cold season, winter, causes the formation of smog, which reduces visibility and causes problems on the roads. Formation of smog is an indication of air pollution. to study the relationship between the amount of available water and the numbers and variety of living organisms. Select a small area near a pond. Count the number of individuals of each plant and animal species in the area. Select a dry place. Count the number of individuals of each plant and animal species in this area. Conclusion. There are much more animal and plant species in the most area than at dry places. To demonstrate the role of plants in checking soil erosion. Materials required: 2 identical trays, soil, germinated gram seeds, beakers with measuring scale, water, wooden cubes. Procedure. Take 2 identical trays A and B and fill them with soil. Plant gram seedlings in tray A and leave the second tray as such. After 6-7 days. Tilt both the trays at an angle with the help of wooden cubes. Make sure that both the trays are tilted at the same angle. Pour equal amount of water gently in both the trays and collect the water flowing out of the trays. Now, note down the amount of soil collected in the beakers from the 2 trays. Observation. You find that the soil in the tray with plants does not get washed down with water. In other words, plants help to prevent soil erosion. To observe the presence of organisms in soil. Materials required: water. Procedure. Select the small area of 1 meter square on the ground. Water the ground with plain water. Conclusion. A number of earthworms and other organisms like insects, larvae, snails, and centipedes come out from the soil. To show the presence of air in the soil. Materials required: glass beaker, dry soil, water-filled beaker, glass rod. Procedure. Take a glass beaker and put some dry soil followed by water in it. Stir the contents with a glass rod. Air bubbles coming out of soil in water. Conclusion. Air bubbles coming out of soil in water, showing the presence of air in the soil.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
To study the change of state from water to steam. Materials required: 100 cc beaker, a thermometer Celsius, a glass stirrer, a wire gauze, a tripod stand, a Bunsen burner, an iron stand, tap water. Method: half fill the beaker with water and place it over a wire gauze and tripod stand. Suspend a Celsius thermometer from the iron stand such that its bulb is well within the water. Place a glass stirrer in the water. Record the temperature of water. Heat the beaker on a low Bunsen flame and continuously stir the water with a glass stirrer. Go on recording the temperature till water starts boiling. Allow the water to boil for a few minutes and record its temperature. You notice that the temperature of water rises till it starts boiling. The temperature of boiling water is 100 degrees Celsius, 373 K. If we continue heating the water, it changes to steam, but the temperature remains constant, that is 100 degrees Celsius, 373 K. Note: the temperature of boiling water may not be 100 degrees Celsius, 373 K, because the boiling point also depends upon the atmospheric pressure, the height of a place from the sea level, etc. To prove that cooling is caused by evaporation. Materials required: an iron stand with clamp, 2 Celsius thermometers, a small piece of muslin cloth, water. Method: suspend the Celsius thermometers A and B from the clamp of an iron stand. Read and record the temperature of each thermometer. You observe that both the thermometers read the same. Now, tie a small piece of muslin cloth to the bulb of thermometer A. Pour a few drops of water on the muslin cloth. Gently blow air on the muslin cloth from your lungs for a minute. Read the temperature of the thermometers. You observe that temperature shown by thermometer A is less than the temperature shown by thermometer B. It is because evaporation of water causes cooling. Thus, the activity clearly proves that cooling is caused by evaporation. Sublimation of ammonium chloride. Materials required: ammonium chloride, a dry hard glass test tube, cotton wool, spirit lamp. Method: place about 2 grams of ammonium chloride in a dry hard glass test tube and plug its mouth with cotton wool. Clamp the hard glass test tube in an iron stand and heat it gently on a spirit lamp. In a few moments, ammonium chloride sublimes, forming dense white fumes which fill the whole tube. Stop heating and allow the test tube to cool. it is seen that the dense white fumes slowly disappear and a fine white powdery deposit of ammonium chloride sticks to the side of the test tube. To study about heterogeneous mixture. Materials required: 4 beakers, 4 glass stirrers, powdered copper sulfate, slake lime, mixture of sand and common salt. Method: divide the class into 4 groups A, B, C and D. Provide a beaker containing 100 cc of water, 2 grams of powdered copper sulfate and a glass stirrer to the group A. Provide a beaker containing 100 cc of water, 5 grams of powdered copper sulfate and a glass stirrer to the group B. Provide a beaker containing 100 cc of water, 2 grams of slake lime and a glass stirrer to the group C. Provide a beaker containing 100 cc of water, 2 grams of mixture of sand and common salt and a glass stirrer to the group D. Ask each group to mix the contents thoroughly and then bring them to your teacher's table. You notice that in case of group A and B, the mixture of copper sulfate and water has a uniform composition, but the color of the solution is more dark in case of group B than in group A. This suggests that a mixture can have variable composition. In case of group C, most of the slake lime settles at the base of the beaker. The water in the beaker has a slight milky color. In case of group D, the sand settles at the base of the beaker, but common salt dissolves. This suggests that the mixture formed in case of C and D are heterogeneous in nature. That is, they do not have the same composition throughout. To study about homogeneous mixture. Materials required: 6 beakers, 6 glass stirrers, 6 funnels, filter papers, 6 torches, water, common salt, powdered copper sulfate, powder chalk, milk, blue-black ink, wheat flour, dropper. Method: divide the class into 6 groups A, B, C, D, E and F. Give each group 1. 2 beakers, 2. a glass stirrer, 3. a funnel, 4. a filter paper, 5. a torch, 6. 50 cc of water. Provide 2 grams of common salt and 2 grams of powdered copper sulfate to the groups A and B respectively. Provide 2 grams of wheat flour and 2 grams of powdered chalk to the groups C and D respectively. Provide few drops of milk and blue-black ink to the groups E and F respectively. Tell all the groups to prepare the mixture in water by stirring thoroughly with the glass stirrer. Tell each group to make the following observations. Are the particles of mixture visible to the naked eye? Do the particles of the mixture tend to settle down after a few minutes? Does the path of light become visible in the mixture when the beam of light is directed on the mixture? Is there any residue left on the filter paper when the mixtures are filtered? Observations. In case of group A and B, neither the particles of the mixture are visible nor do they settle down after a few minutes. The path of light is not visible through the mixtures and no residue is left on the filter paper on filtration. Such a mixture is homogeneous and is called a solution. In case of groups C and D, the particles of the mixture are visible and they tend to settle down after a few minutes. The path of light is visible through the mixtures and a residue is left on the filter paper on filtration. Such a mixture is called a suspension. In case of groups E and F, the particles of the mixture are not visible and they do not settle down after a few minutes. The path of light is visible through the mixtures and no residue is left on filter paper on filtration. Such a mixture is called a colloidal solution or a colloid. To study about saturated and unsaturated solution. Materials required: 200 cc beakers, common salt, potassium nitrate, Bunsen burner, water, glass stirrer, teaspoon. Method. Take 200 cc beakers and pour 50 cc of water in each of them. Label the beakers A and B. In the beaker A, pour 1 level teaspoonful of common salt, and in the beaker B, pour 1 level teaspoonful of potassium nitrate. Stir the contents well. When the salts dissolve in both the beakers, add 1 level teaspoonful of common salt and potassium nitrate to each of the beaker and stir well. Continue adding common salt and potassium nitrate to the respective beakers till they stop dissolving. You notice that more teaspoonful of potassium nitrate are required as compared to common salt. This shows that different substances have different solubilities in the same amount of water. Now, heat each beaker separately and add more amount of substances, solutes, till the water is about to boil and the salt stops dissolving. You notice that on heating, more amount of solutes dissolve in the same amount of water till a stage is reached when they stop dissolving. Allow the contents of both the beakers to cool for a few hours. After a few hours, you notice that crystals of solutes settle at the base of the liquid. Conclusion. From this, we can conclude that the solubility of a solute decreases with the fall in temperature. The extra solute, which dissolves at a higher temperature, comes out of its solution in the form of crystals on lowering the temperature. To study about Tyndall effect. Note: the phenomenon due to which the path of light becomes visible due to scattering of light by the colloidal particles is called Tyndall effect. Materials required: a wooden box containing convex lens on one side and a microscope on the other side. Beaker containing soap solution. Source of light. Method: take a wooden box which is fitted with a convex lens on one side and a microscope on the other side, such that the convex lens and the objective lens of the microscope face each other. Place a beaker containing soap solution inside the wooden box. Place a powerful bulb on the side of convex lens and move it backward or forward till a narrow parallel beam of light is formed. Look through the microscope. You observe individual colloidal particles surrounded by a cone of bluish light. The bluish cone of light is called Tyndall cone. Separating the components of mixture through evaporation. Definition: the process of evaporation is suitable for the separation of non-volatile soluble solid from its liquid solvent, water. Materials required: sand, tripod stand, Bunsen burner, china dish, common salt solution. Procedure: heat the sand in an iron vessel by placing it over a tripod stand. This arrangement is called sand bath. Place a china dish on the sand bath. Pour about 50 cc of the common salt solution into the china dish. The heat gently evaporates water from the solution such that water does not boil. In a few minutes, the water evaporates, leaving behind dry common salt. This method is suitable for the following solid-liquid mixtures: solid-liquid mixture, non-volatile solid, liquid, potassium chloride and water, potassium chloride, water, sodium nitrate and water, sodium nitrate, water, copper sulfate and water, copper sulfate, water. Separating the components of a mixture by centrifugation. Definition: the method of separating finely suspended particles in a liquid by whirling the liquid at a very high speed is called centrifugation. Principle of centrifugation. It is based on the principle that when a very fine suspension or a colloidal solution is whirled rapidly, the heavier particles are forced towards the bottom of the liquid and the lighter particles stay at the top. Materials required: full cream milk, test tubes, laboratory centrifuge. Procedure: pour full cream milk in the test tube with a pivot in your laboratory centrifuge. Shut the lid of the centrifuge and switch on the current. When the centrifuge starts working, the tube containing milk swings out into the horizontal position and whirls around its axis at a high speed. The centrifugal pull, the outward pull, pushes the heavier particles outward. that is, towards the bottom of the mixture. Thus, the heavier particles of proteins, carbohydrates, etc. are pushed towards the bottom of the tube, but the lighter particles of the fat stay near the top of the tube and hence separate. Separating the components of a mixture by a separating funnel. Note: the separation of the two immiscible liquids is based on the difference in their densities. Materials required: separating funnel, iron stand, immiscible liquid mixture, 2 conical flasks. Procedure: close the tap of the separating funnel and clamp it in a vertical position in an iron stand. Pour the immiscible liquid mixture, say benzene water mixture, in a separating funnel. Allow the mixture to stand for half an hour or more. After half an hour, the immiscible components of the mixture, that is benzene and water, separate out into 2 distinct layers. Benzene forms the lighter layer on the top and water forms the heavier layer at the bottom. Place a conical flask or a beaker under the nozzle of the separating funnel. Turn the stopcock gently so that water trickles in the flask or the beaker drop by drop. Once the water is drained out, close the stopcock. Now, place another conical flask or a beaker under the nozzle of the separating funnel. Open the stopcock to drain out benzene. The given table shows different immiscible liquids which can be separated by using a separating funnel. Immiscible liquid, liquid mixture. Heavier liquid, lighter liquid. Kerosene oil and water, water, kerosene oil. Turpentine oil and water, water, turpentine oil. Chloroform and water, water, chloroform. Mustard oil and water, water, mustard oil. Separating the components of a mixture by sublimation. Definition: this method is used in the separation of such solid-solid mixtures where one of the components sublimes on heating. However, it is useful only if the components of the mixture do not react chemically on heating. Materials required: mixture of common salt and ammonium chloride, china dish, Bunsen burner, glass funnel, tripod stand with wire gauge, cotton wool, paper, glass rod. Procedure: place a mixture of common salt and ammonium chloride in a china dish and heat it over a low Bunsen flame. Place a clean glass funnel in an inverted position in the china dish and close the mouth of its stem with cotton wool. Ammonium chloride in the mixture sublimes to form dense white fumes. These fumes condense on the cooler sides of the funnel in the form of fine white powder. When the mixture gives off no more white fumes, lift the funnel, scrap the fine white powder from its sides on a piece of paper. This is pure ammonium chloride. The residue left behind in the funnel is sodium chloride. The given table shows the list of mixtures which can be separated by the process of sublimation. Solid-solid mixture, sublimable solid, sand and iodine, iodine, common salt and iodine, iodine, sodium sulfate and benzoic acid, benzoic acid, iron fillings and naphthalene, naphthalene. Fractional distillation, a method of separating liquids from a mixture. Note: the process of separation of two miscible liquids by the process of distillation makes use of the difference in their boiling points is called fractional distillation. The process of fractional distillation is useful only when the difference in the boiling points of the two liquids is 20 degrees centigrade or more. The process of fractional distillation is similar to the process of distillation, except that here we use a fractionating column. Materials required: iron stand, conical flask, distillation flask, fractionating column, tripod stand, wire gauge, thermometer, mixture of alcohol and water, Bunsen burner, a rubber cork, Liebig's condenser. Procedure. The design of fractionating column is such that the vapors of one liquid with higher boiling point are preferentially condensed as compared to the vapors of another liquid with lower boiling point. When the mixture of vapors of alcohol and water pass through the fractionating column, the water condenses and flows back in the flask, while the vapors of alcohol pass on. In Liebig's condenser, the alcohol vapors liquefy and flow into the flask as distillate. Pure water remains in the flask. To make the water fit for city water supply. River water is normally used to supply drinking water to big cities. This water is unfit for drinking purposes, as it contains a large amount of suspended impurities and harmful microorganisms, such as bacteria and germs. The river water is purified in the following stages. A. Sedimentation. The water is allowed to stand in big tanks, where heavier suspended impurities settle down. To increase the rate of sedimentation, alum is added to it, loading. The impurities settle at the bottom. B. Filtration. The semi-clear water is allowed to pass through the beds of sand, charcoal and gravel to remove the suspended impurities. C. Removal of harmful microorganisms or sterilization. The harmful bacteria in filtered water can cause very serious diseases such as typhoid, cholera, jaundice, dysentery, etc. Thus, bleaching powder or chlorine gas is added to the filtered water. This kills the microorganisms and hence the water becomes fit for drinking. This water is directly pumped into the overhead tanks for supply to a city. Law of conservation of mass. According to this law, mass can neither be created nor destroyed in a chemical reaction. Experiment. Pour about 20 ml of solution of silver nitrate in a clean conical flask. Take an ignition tube and tie a long thread to its neck. Half fill the ignition tube with concentrated hydrochloric acid. Carefully lower the ignition tube in the conical flask, taking care that its contents do not spill in the silver nitrate solution. Fix a rubber cork in the mouth of the conical flask so that the ignition tube remains suspended above the silver nitrate solution. Find the mass of the conical flask by a physical balance and record it. Now, tilt the conical flask so that the contents within it mix. You will notice that a curdy white precipitate is formed. It is because silver nitrate reacts chemically with hydrochloric acid to form curdy white silver chloride and nitric acid. Find the mass of the conical flask again and record it. You will notice that there is no change in the mass, thereby proving the law of conservation of mass. In the above experiment, Lavoisier demonstrated the importance of careful measurement of mass, which led to the discovery of another law, the law of constant proportions. Thomson's atomic model. With the discovery of electrons and protons, it was important to know how these particles are arranged within an atom. The atomic model proposed by J.J. Thomson at that time is called apple pie pudding model. J.J. Thomson believed that an atom is made up of positively charged substance in the form of a sphere. Into this sphere are embedded electrons much the same way as the apples are embedded in an apple pie. Furthermore, the total positive charge of the sphere is equal to total negative charge of the electrons, and hence the atom remained electrically neutral. J.J. Thomson's model of the atom was not accepted by fellow physicists, as it was unable to explain how positively charged particles were shielded from negatively charged particles without getting neutralized. Discovery of the nucleus. Rutherford's experiment. In order to test J.J. Thomson's atomic model, Rutherford set up the following experiment. He reasoned that if positively charged mass present within the atom is thinly spread, then any positively charged particle moving with sufficient kinetic energy would easily penetrate through it. Thus, if a thin foil of gold is exposed to fast-moving positively charged particles, then the particles should just pass through the foil. These particles can be detected by zinc sulfide screen placed behind the gold foil when scintillations are produced on the screen. Rutherford selected alpha particles as missiles to hit the atoms. Alpha particles are the nuclei of helium, He2 positive, having mass of 4 AMU and 2 units of positive charge. It is a nucleus consisting of 2 protons and 2 neutrons. The alpha particles were obtained from radium and then accelerated. These accelerated particles were condensed to a narrow beam by passing them through positively charged parallel plates. They were finally directed against a very thin gold foil placed at the center of a circular zinc sulfide screen. Rutherford expected the alpha particles to pass through the gold foil and produce bright scintillations at point A. However, to his surprise, some of the scintillations were produced in regions BB and CC. These observations can be explained only if we assume that positive charge in the atom is concentrated in a very small place within the atom. Following is the summary of Rutherford's experiment. Most of the alpha particles passed through the foil straight without suffering any change in their direction. A small fraction of alpha particles deflected through small angles and few through large angles. 1 out of 12,000 particles appeared to rebound. In other words of Rutherford, this result was almost incredible, as if you fire a 15-inch shell at a piece of tissue paper, and it comes back and hits you. Rutherford called this concentrated positively charged mass within the atom, nucleus, and the particles present within the nucleus, nucleons. When alpha particles approach this concentrated positive mass at right angles, they get deflected almost through 180 degrees. However, if they pass very close to the concentrated positive mass, they get deflected through large angles. Much the same way, if they pass just close to the concentrated positive mass, they get deflected through small angles. But if they do not pass close to the concentrated positive mass, they do not get deflected. That is, they just pass through the gold foil. As most of the alpha particles are able to pass through the gold foil, producing strong scintillation at A, the following conclusions can be drawn from the experiment. The nucleus of an atom is positively charged. The atom, on the whole, is relatively empty, and the positively charged mass in the nucleus is concentrated over a very small space. Nucleus of the atom is very dense and hard. The angle through which alpha particles get scattered depends upon the angle at which they approach the positively charged nucleus of the concentrated mass. Drawback of Rutherford's atomic model. The comparison of electrons to the planets in the solar system is the main drawback of the Rutherford's atomic model. It has been found that if an electrically charged particle revolves around a circular path, then it always radiates out energy. Thus, if an electron moves around the nucleus, it must continuously radiate out energy and hence gradually move towards the nucleus in a spiral path till it collides with the nucleus. However, we know that the atom is very stable. Rutherford's model cannot explain this stability. Bohr's model of an atom. In 1930, Niels Bohr, a young Danish physicist, suggested that the classic laws of mechanics and electrodynamics cannot be used to describe the motion of electrons around the nucleus. He suggested that the electrons revolving around the nucleus are confined to a certain fixed orbits, shells or energy levels, and envelop the nucleus much the same way as the skin of an onion. The electrons do not lose any energy while revolving around the nucleus. He further suggested that electrons cannot move in the areas between the two orbits. He called these areas forbidden territories. He suggested that an electron revolving in some particular orbit on gaining certain fixed amount of energy can jump to the next orbit and vice versa. However, the electron will not position itself in between the space of the two orbits. For moving from one orbit to another orbit, the electrons have to absorb or radiate out some fixed amount of energy. Therefore, these orbits are called energy levels. For the sake of convenience, the orbits, shells, or energy levels are given specific names or numeral values. If an electron is revolving in the shell closest to the nucleus, then that electron is called the K electron, and the shell in which it is revolving as the K shell. The various shells and energy levels are K, L, M, N, O, and so on. Bohr's-Bury scheme of electronic configuration. A. The maximum number of electrons which can be present in any shell of an atom is given by the formula 2n square, where n is the number of the shell as counted from the nucleus. Thus, according to the above formula, maximum number of electrons in the first shell, K shell, is equal to 2n square, that is equal to 2 1 to the power 2 equal to 2. Maximum number of electrons in the second shell, L shell, is equal to 2n square equal to 2 2 to the power 2 equal to 8. Maximum number of electrons in the third shell, M shell, 2n square equal to 2, 3 square equal to 18. Maximum number of electrons in the fourth shell, N shell, is equal to 2n square equal to 2, 4 square equal to 32. B. The outermost shell cannot have more than 8 electrons and the last but one shell cannot have more than 18 electrons. C. It is not necessary for a given shell to complete itself before another shell starts forming. As a rule, the new shell is formed as soon as the outermost shell attains 8 electrons. D. An atom becomes stable. It stops reacting chemically with other elements when its outermost shell has 8 electrons or it has only one shell containing 2 electrons. Geometric representation of atomic structure of some elements. Element, number of neutrons, A to Z, number of protons, number of electrons, electronic configuration, geometric representation of atomic structure. Hydrogen H, 1 minus 1 equal to 0, 1, 1, 1. Helium He, 4 minus 2 equal to 2, 2, 2, 2. Lithium Li, 7 minus 3 equal to 4, 3, 3, 2, 1. Beryllium Be, 9 minus 4 equal to 5, 4, 4, 2, 2. Boron 11B5, 11 minus 5 equal to 6, 5, 5, 2, 3. Carbon 12C6, 12 minus 6 equal to 6, 6, 6, 2, 4. Nitrogen 14N7, 14 minus 7 equal to 7, 7, 7, 2, 5. Oxygen 16O8, 16 minus 8 equal to 8, 8, 8, 2, 6. Fluorine 19F9, 19 minus 9 equal to 10, 9, 9, 2, 7. Neon 20Ne10, 20 minus 10 equal to 10, 10, 10, 2, 8. Sodium 23Na11, 23 minus 11 equal to 12, 11, 11, 2, 8, 1. Magnesium 24Mg12, 24 minus 12 equal to 12, 12, 12, 2, 8, 2. Aluminium 27Al13, 27 minus 13 equal to 14, 13, 13, 2, 8, 3. Silicon 28Si14, 28 minus 14 equal to 14, 14, 14, 2, 8, 4. Phosphorus 31p15, 31 minus 15 equal to 16, 15, 15, 2, 8, 5. Sulfur 32s16, 32 minus 16 equal to 16, 16, 16, 2, 8, 6. Chlorine 35Cl17, 35 minus 17 equal to 18, 17, 17, 2, 8, 7. Argon 40Ar18, 40 minus 18 equal to 22, 18, 18, 2, 8, 8. Potassium 39K19, 39 minus 19 equal to 20, 19, 19, 2, 8, 8, 1. Calcium 40Ca20, 40 minus 20 equal to 20, 20, 20, 2, 8, 8, 2. Isotopes. Definition: atoms of the same element having same atomic number but different mass numbers are called isotopes. Examples: hydrogen has 3 isotopes. They are protonium or ordinary hydrogen, deuterium and tritium. The mass numbers, atomic numbers and the number of neutrons are: protonium, ordinary hydrogen, H, 1H1, 1, 1, 1 minus 1 equal to 0. Deuterium, D, 2H1, 2, 1, 2 minus 1 equal to 1. Tritium, T, 3H1, 3, 1, 3 minus 1 equal to 2. Chlorine has 2 isotopes, 35Cl17 and 37Cl17. The mass number, atomic number and the number of neutrons of these isotopes are 35Cl17, 35, 17, 17, 17, 2, 8, 7, 35 minus 17 equal to 18. 37Cl17, 37, 17, 17, 17, 2, 8, 7, 37 minus 17 equal to 20. Carbon has 2 common isotopes, 12C6 and 14C6, which differ from one another by 2 neutrons. Oxygen is mainly 16O8. However, it has 2 isotopes, 17O8 and 18O8. Neon is mainly 20Ne10. However, it has 2 isotopes, 21Ne10 and 22Ne10. To prove that the particles of matter are in a state of continuous motion. Materials required: a fresh agarbatti, incense stick, a stand to hold agarbatti, a match stick. Method: take out a fresh incense stick from a pack and fix it in a stand. Place the stand in the corner of a room. You will be able to smell its perfume. Now, slowly move away from the incense stick. You notice that you cannot smell the perfume. Now, light the incense stick and leave the room for a few minutes. On entering the room, you will be able to smell the perfume everywhere in the room. Let us try to answer the following questions. Questions. Why can you smell the perfume of incense stick? Why you cannot smell its perfume at a short distance when the incense stick is not lighted? Why does the smell of perfume of incense stick fill the whole room in a few minutes when lighted? Answer. The particles of perfume matter are not stationary but are continuously moving. They drift through the air and hence we can smell the perfume. The particles of the perfume matter do not have sufficient energy to drift through the air. Thus, we cannot smell it when we are at a few steps away from the incense stick. When the incense stick is lighted, the heat energy makes the particles of the perfume to move rapidly. Thus, they easily drift through the air in the room and hence we can smell it anywhere in the room. From the above activity, the following conclusions can be drawn. Particles of matter are in continuous state of motion and hence have some energy. When the temperature of matter rises, the particles of matter move faster. Diffusion. The intermixing of particles of two substances on their own is called diffusion. In the above activity, the particles of perfume diffuse into the particles of air on their own and hence we can smell them. When the incense stick is lighted, the particles of perfume have more energy. They diffuse rapidly in air present in the room and hence we can smell them everywhere in the room. To prove that particles of matter attract each other. Materials required: an iron nail, a small piece of wood, rubber band, knife, hammer. Method. Take an iron nail, a small piece of wood and a rubber band. Try breaking them by cutting, hammering or stretching. You notice that the rubber band is the easiest to break, followed by wood and then iron. There are some forces which keep the particles of matter together. However, the strength of these forces varies with the kind of matter in a given substance. This force of attraction exists between the smallest particles of matter and is commonly called intermolecular force. To study the diffusion of two different liquids in water. Materials required: 200 cc beakers filled with water, 2 droppers, honey, blue-black ink. Method. Fill the dropper with blue-black ink. Allow 1 drop of the ink to trickle into the first beaker, by letting it fall on the upper rim of the inner side of the beaker. Cover the beaker and leave it undisturbed for 4 hours. Make observations after every 15 minutes and record them. As the drop of ink trickles along the sides of the beaker, the blue color of the ink starts diffusing in water, which appears like wavy blue streaks in water. The ink spreads evenly in water in about 2 hours. In the second beaker, add a drop of honey on the inner side of the beaker and make observations as stated above and record them. The honey drop continues traveling along the side of the beaker and there is no visible diffusion of it in water. The diffusion of honey is very slow as compared to the diffusion of ink. It is because the honey is a dense liquid. Its particles have strong intermolecular forces as compared to water. Thus, it diffuses slowly in water. To study diffusion of a solid in a water at room temperature. B. Boiling hot water. Materials required. 200 cc beakers water at room temperature. Boiling hot water. 2 small crystals of potassium permanganate. Method. Fill one beaker with tap water at room temperature and the other beaker with boiling hot water. Drop one crystal of potassium permanganate in cold water and the other crystal in boiling hot water. Record your observations in both the beakers for half an hour. Observations. Dense and deep violet color is formed around each crystal. However, the size of deep violet color in hot water is larger than that in cold water. The dense violet color starts diffusing slowly into cold water in the form of colored streaks. Gradually, the solution changes to pink color, which is darker nearer the base of the beaker. In case of hot water, the dense violet color rapidly diffuses to form pink color, which is more homogeneous as compared to that in cold water. The rate of diffusion increases with the temperature. It is because boiling hot water molecules have more kinetic energy and there are larger intermolecular spaces. Thus, the particles of solid potassium permanganate rapidly diffuse and hence rate of diffusion increases. Conclusion. The rate of diffusion of a solid in a liquid increases with a rise in temperature. To study diffusion of gases in water. Materials required. 200 cc beakers half filled with tap water, wire gauze, tripod stand, Bunsen burner. Method. Place the wire gauze over the tripod stand and then the beaker containing water. Heat the beaker by a Bunsen burner on a low flame. Do not allow the water to boil. Make your observations as the water is being heated. Observations. Tiny bubbles of gas cling to the sides of the beaker. The tiny bubbles are of air, especially carbon dioxide and oxygen, which got dissolved in water naturally. These gases are expelled out when water is warmed. The gases like oxygen and carbon dioxide diffuse and hence dissolve in water. The dissolved oxygen in water is essential for respiration of water animals. The dissolved carbon dioxide helps the water plants to synthesize their food by the process of photosynthesis. Conclusions. The rate of diffusion of gas in a liquid decreases with a rise in temperature. To show that gases are far more compressible as compared to liquids. Materials required: 250 ml syringes, 2 plastic corks, water. Method: take a syringe, remove its plunger outward. Close the nozzle of the syringe with a plastic cork. Fill half of the syringe with water. Now, push the plunger inward with maximum force and record your observation. Stop applying force and again record your observation. The plunger does not move inward on the application of force. When the force is removed, the plunger does not move backward. Reason: liquids have small intermolecular spaces, thus they cannot be compressed. Take another syringe. Remove the plunger outward. Close the nozzle of the syringe with a plastic cork. Fill half the syringe with air. Now, push the plunger inward with maximum force and record your observation. Stop applying force and again record your observation. The plunger moves downward to a considerable length on the application of force. When the force is removed, the plunger moves backward and takes its original position. Reason: gases have large intermolecular spaces. Thus, they easily get compressed on the application of force. The compressed gases are under high pressure. When the force is removed, this high pressure forces the plunger back to its original position. To study the change of state of ice to water. Materials required: 100 cc beaker, a thermometer, Celsius, a glass stirrer, a wire gauze, a tripod stand, a Bunsen burner, an iron stand, ice cubes. Method: half fill the beaker with ice cubes and place it over a wire gauze and a tripod stand. Suspend a Celsius thermometer from the iron stand such that its bulb is well within the ice. Place a glass stirrer in the ice. Record the temperature of ice. You find that it is 0 degrees Celsius, 273 K. Now, heat the beaker on a low Bunsen flame and continuously stir the contents of the beaker. Record the temperature 5 to 6 times till all the ice melts. You observe that the temperature remains 0 degrees Celsius, 273 K throughout, till all the ice melts.
Goyal Brothers to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
Kinds of velocity. A. Uniform velocity. Consider a moving body at point A such that it travels towards east in a straight line and covers distances AB is equal to BC is equal to CD is equal to 2 meter in time intervals of 1 second each. When a body describes a motion as stated above, it is said to be moving with uniform velocity. Definition: when a body covers equal distances in equal intervals of time, however smaller intervals may be, in a specified direction, the body is said to be moving with a uniform velocity. Conditions for uniform velocity: the body must cover equal distances in equal intervals of time. The direction of motion of the body should not change. B. Variable velocity or non-uniform velocity. Definition: when a body covers unequal distances in equal intervals of time in a specified direction, or when a body covers equal distances in equal intervals of time, but its direction changes, then the body is said to be moving with variable velocity. A moving body at A, it covers distances AB equal to 10 meter in 1 second, BC is equal to 5 meter in 1 second, and CD is equal to 15 meter in 1 second in the same direction, that is east. As the body is covering unequal distances in equal intervals of time, it is moving with the variable velocity. Let a moving body is at A. It is moving in a circular path and is covering distances AB equal to BC equal to CD equal to AD equal to 5 meter in the time intervals of 1 second each. Thus, the body is moving with a uniform speed of 5 meter per second. However, the direction of motion of the body continuously changes along the circular path. Thus, although the body has a uniform speed, yet it has a variable velocity. Conditions for variable velocity: either of the following two conditions should be satisfied by a moving body with the variable velocity. 1. It should cover unequal distances in equal intervals of time in a specified direction. Or 2. It should cover equal distances in equal intervals of time, but its direction must change. Newton's law of gravitation. Definition: every body in the universe attracts every other body with a force, which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Mathematical expression for Newton's law of gravitation. Consider two bodies A and B of masses m and m respectively, such that d is the distance between their centers. Let F be the force by which these bodies mutually attract each other. Then, according to Newton, F is proportional to m into m. Statement 1. F is proportional to 1 by d square. Statement 2. Combining statement 1 and statement 2, we have F is proportional to m into m divided by d square, or F is equal to g into m divided by d square, when g is the constant of proportionality, commonly called the universal gravitational constant. It has been found that the value of gravitational constant does not depend upon the masses of the bodies, the distance between the bodies, the medium between the bodies. The formula for gravitational force is applicable anywhere in the universe.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
Mathematical expression for work. Consider a body A acted upon by a force F such that the body gets displaced through a distance s in the direction of applied force. If W is the work done by the body, then W is proportional to F, statement 1. W is proportional to S, statement 2. Combining statement 1 and statement 2, we have W is proportional to F into S, or W is equal to K into F into S, statement 3, where K is the constant of proportionality. If the body is acted upon by a unit force which causes a unit displacement such that the work done by the body is 1 unit, then from statement 3 we get 1 is equal to K into 1 into 1, or K is equal to 1, statement 4. Substituting the value of K in statement 3, we have W is equal to F into S. Thus, mathematically, the work is the product of force and the displacement caused by the force in its own direction. It must be kept in mind that work is a scalar quantity. Positive and negative work. Positive work. Definition. When the applied force causes displacement in its own direction, the work done is said to be positive work. Consider a situation in which applied force F acting on a block in position A displaces it to position B and in doing so causes a displacement S. Now, as the displacement is caused in the direction of applied force, therefore work done W is the product of applied force and displacement. W is equal to F into S. In such a situation, the work done by the applied force is taken as positive. Negative work. Definition. When a force acting on a body is opposite to the direction of displacement of the body, then the work done is said to be negative. However, if we consider the forces acting on the block in totality, then there is force of friction F acting at an angle 180 degree to the applied force. In such a situation, the work done by the force of friction will be W equal to minus F into S. The minus sign denotes that force is acting opposite to the direction of displacement. Thus, the work done by the force of friction is negative. Similarly, when block of mass m, weight mg is raised through the height h against the acceleration due to gravity g, then positive work done by the applied force is equal to mg into h. At the same time, the negative work done by the force of gravitation, which is opposite to the direction of displacement, is as below. Negative work done by the force of gravitation is equal to minus mgh. Zero work. No work is done when a force acts at right angles to the direction of displacement. It is because in such a situation displacement in the direction of force is zero. It is for the same reason that when a person carrying a suitcase vertically in his hand walks in a horizontal direction, no work is done, because the angle between the direction of force applied by hand and the direction of displacement is 90 degrees. Similarly, a body moving in a circular path does no work because the force always acts at right angles to the direction of displacement of the body. Thus, we can say that the satellites going around the Earth do no work. Work done by the forces in moving satellite around the Earth is zero. Similarly, the Earth revolving around the Sun is not doing any work. Here, you can always ask that what happens to the gravitational force which the Earth exerts on the satellites or Sun exerts on the Earth. Well, this force continuously changes the direction of satellites or the Earth respectively, otherwise they will shoot out of their orbits. Mathematical expression for potential energy. Consider a stone of mass m, initially at ground level, raised vertically upward through height h against the force of gravity, such that acceleration due to which is g. Now, force acting on the stone is equal to mg. Therefore, total work done in lifting the stone is equal to force into distance is equal to mgh. But the total amount of work done in lifting the stone is equal to energy spent. Therefore, energy spent in lifting the stone is equal to mgh. As the energy spent in lifting the stone is stored within the stone in the form of potential energy, therefore potential energy is equal to energy spent in lifting the stone. PE is equal to mgh. It is useful to note that potential energy, work done against gravity, of a body depends upon vertical heights between the initial and final positions of the body and not the path along which an object is raised. For example, you can raise a bag of 20 kg to the top floor of building 10 meter high by pulling it vertically upward with a rope or by taking it upward through a staircase. In either of the cases, the potential energy in bag will be same as it is raised through the same height. Mathematical expression for kinetic energy. Consider a body of mass m at A such that its initial velocity is v. Let the body roll on the floor such that it stops after covering a distance s. As the body stops, there must be some retarding force acting on the body. If we could calculate the retarding force and then multiply it with the distance covered by the body, we get the measure of work done in stopping the body. This measure of work will be numerically equal to the kinetic energy of the body at A. Applying v square minus u square is equal to 2as. 5 0 square minus v square is equal to 2as. Final velocity is 0. Or A is equal to minus v square divided by 2s. Therefore, retardation acting on the body is equal to minus A is equal to minus v square divided by 2s equal to v square divided by 2s. Therefore, retarding force acting on the body is equal to mass into retardation is equal to m into v square divided by 2s. Therefore, work done by the retarding force in stopping the body is equal to retarding force into distance equal to mv square divided by 2s into s is equal to mv square divided by 2. But work done by retarding force in stopping the body is equal to kinetic energy of the body at A. Therefore, kinetic energy of the body is equal to mv square divided by 2, or kinetic energy is equal to half mv square. Sound is produced by vibrating bodies. 1. Stretched wire. 2. Turning fork. Materials required: 2 iron nails, thin nichrome wire about 50 cm, V-shaped paper, pith ball, tuning fork, rubber hammer. Procedure: 1. Stretched wire. Take a thin nichrome wire about 50 cm long and stretch it between 2 nails tightly. Pluck the wire. A sound is heard. Now place a V-shaped paper rider on the vibrating wire. It is observed that paper flies off, thereby proving that the sound is produced by the vibrating bodies. 2. Turning fork. Take a tuning fork. It is a U-shaped fork of steel having a handle. Strike the tuning fork with a rubber hammer and hold it close to the ear. A sound is heard. Now take a freely suspended pith ball and touch one end of tuning fork, which is already hit with a rubber hammer, to it. It is observed that pith ball repeatedly flies outward. This experiment too proves that the sound is produced by a vibrating body. Formation of circular ripples on water. Materials required: beaker, water, tuning fork, rubber pad. Procedure: fill a 50 cc beaker with water up to the brim. Take a tuning fork and strike it against a rubber pad so as to set it into vibrations. Gently touch one of the vibrating prongs to the surface of water. You observe that ripples are formed on the surface of water which travel outward. The reflected light on the wall moves up and down on producing loud sounds. Materials required: discarded soft drink can, tin cutter, rubber balloon, glue stick, aluminium foil, torch. Procedure: take a discarded soft drink can such as Coca-Cola can or Pepsi-Cola can and remove its both end with the help of a tin cutter so as to make a hollow tube. Wash the can and then on its one end fix a thin sheet of rubber balloon. In the middle of the stretched sheet of balloon, fix a small piece of aluminium foil with the help of glue. The aluminium foil acts as a mirror. With the help of a friend, allow the light from the torch to pass through the cardboard slit. Adjust the can such that the light coming from the torch falls on the wall. Now shout loudly at the other end of the can. You observe that light on the wall rapidly shifts. It is because the rubber membrane vibrates rapidly, and in doing so makes the aluminium foil vibrate. The light falling on aluminium foil on reflection changes its position because of these vibrations.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
Propagation of sound. Suspend pendulums A, B, C, D, E, F, and G from a tightly stretched wire, such that their bobs are touching one another. Stretch the pendulum A to the position X and release it. You notice that when this pendulum strikes the bob of pendulum B, the bob of pendulum G moves to the position Y. When the bob of pendulum G strikes back the bob of pendulum F, the bob of pendulum A moves towards X. This continues for a few moments. To prove that sound needs material medium for their propagation. Materials required: a cell, a switch, an electric bell arranged inside a bell jar, evacuating pump. Procedure: an electric circuit consisting of a cell, a switch, and electric bell is arranged inside a bell jar with the help of cork, which stands on the platform of an evacuating pump. The switch of the bell is pressed close to the electric circuit. Sound is heard when there is air within the bell jar. Air is now gradually pumped out of the bell jar. The intensity of sound goes on decreasing, and no sound is heard when the air is completely removed from the bell jar. It is because the medium air, which has to carry energy from the bell to the bell jar, is removed. Laws of inertia. Materials required: glass tumbler, a thick cardboard, 1 rupee coin. Procedure: place a thick cardboard on a glass tumbler and over it place a 1 rupee coin. Flick the cardboard with your fingers. You notice the cardboard moves away, but the coin falls in the glass tumbler. Reason: initially, the cardboard and the coin were in the state of rest. When the cardboard is suddenly set into motion due to the flick of fingers, the coin, on account of the property of inertia of rest, continues in its state of rest. Thus, the coin is left behind and hence drops into the glass tumbler. To show the reflection of sound. Materials required: smooth polished wooden board, wooden screen, 2 highly polished tubes from inside. Watch. Procedure. Take a smooth polished large wooden board and mount it vertically on the table. At right angle to the board, fix a wooden screen. On each side of the screen, place a long, narrow and highly polished tube from inside. Place a watch at the end of tube A. Move the tube B slightly left or right till a distinct tick of the watch is heard. Measure the angle PCN and angle RCN between the tubes and the normal. Angle of incidence, angle PCN. Angle of reflection, angle RCN. 30 degree, 30 degree, 40 degree, 40 degree, 45 degree, 45 degree, 50 degree, 50 degree, 60 degree, 60 degree. It is found that angle PCN is equal to angle RCN. This experiment illustrates the laws of reflection. Sonar. Sonar is a device fitted in sailing ships, trawlers, warships, etc. to locate submarines or shoals of fish or depth of ocean bed. To find the depth of an ocean, a strong ultrasonic wave from the ship is sent towards the bottom of ocean. On striking the bottom of ocean, the ultrasonic wave is reflected upward towards the ship. The reflected wave is received by a suitable receiver. The time taken by the wave to travel from the source of sound to the receiver is recorded, that is, 2.4 seconds. Knowing the velocity of sound in water, that is 1450 meter per second, the depth of ocean flow is calculated by the following formula. Depth of ocean flow is equal to velocity of sound in seawater into time divided by 2. Depth of ocean flow is equal to 1450 meter per second into 2.4 second divided by 2 is equal to 1740 meter. Practical applications of reflection of sound. A. Megaphone or speaking tube. When you have to call someone at a far-off distance, say 100 meter, what do? You cup your hands and call the person with maximum sound you can produce. Why do you cup your hands? It is because the hands prevent the sound energy from spreading in all directions. In the same way, the people use horn-shaped metal tubes, commonly called megaphones, while addressing a group of people in fair or tourist spots. Similarly, the loudspeakers used at public address system have a horn-shaped opening. In all such devices, the sound energy is prevented from spreading out by successive reflections from the horn-shaped tubes. B. Ear trumpet or hearing aid. Ear trumpet is a device which is used by the persons who are hard of hearing. Its shape is like a trumpet. The narrow end of it is kept in the ear hole of the person who is hard of hearing, whereas the wider ends faces the speaker. The waves received by the wider end of the trumpet are reflected into the narrow end. This in turn increases the intensity of sound energy, and hence the person who is hard of hearing can hear clearly. C. Sounding board. The sound waves obey the laws of reflection on the plane as well as curved reflecting surfaces. In order to spread sound evenly in big halls or auditoriums, the speaker S is fixed at a principal focus of the concave reflector. This concave reflector is commonly called sounding board. The sound waves on striking the sounding board get reflected parallel to the principal axis. In other words, the sound waves do not spread in all directions. Thus, sounding boards can be placed on the walls of big halls in such a way that everyone in the auditorium hears clearly. D. Stethoscope. It is an instrument used by the doctors for listening sounds produced within the body, especially in the heart and lungs. In a stethoscope, the sound produced within the body of a patient is picked up by a sensitive diaphragm and then reaches the doctor's ears by multiple reflection. Law of conservation of momentum. Definition: in a given system, the sum total of momentum is a constant quantity provided no external force acts on the body, or in a given system, when two or more bodies interact and no external force acts on them, the total momentum of all the bodies is conserved. Mathematical proof of law of conservation of momentum. Consider two marbles A and B of masses m1 and m2 rolling towards each other with the velocities u1 and u2 respectively, such that no other force is acting on them. Now, consider that these marbles collide with each other, such that time of collision is 40 seconds. After the collision, let us imagine the velocity of marble A is v1 and the marble B is v2 respectively. Therefore, change in momentum of marble A in time t seconds is equal to m1 v1 minus m1 u1 equal to m1 v1 minus u1. Therefore, rate of change of momentum of marble A is equal to m1 v1 minus u1 divided by t. As the rate of change of momentum of marble A is the force exerted by the marble B on the marble A, therefore, force exerted on the marble A is equal to F1 equal to m1 v1 minus u1 divided by t. Statement 1. Similarly, change in momentum of marble B in time t seconds is equal to m2 v2 minus m2 u2 equal to m2 v2 minus u2. Therefore, rate of change of momentum of marble B is equal to m2 v2 minus u2 divided by t, as the rate of change of momentum of marble B is the force exerted by the marble A on the marble B. Therefore, force exerted on the marble B is equal to F2 is equal to m2 v2 minus u2 divided by t. Statement 2. Now, by Newton's third law, forces exerted by the marbles on each other are equal and opposite. Therefore, force exerted on the marble A is equal to minus force exerted on the marble B. That implies F1 is equal to minus F2. That implies m1 v1 minus u1 divided by t is equal to minus m2 v2 minus u2 divided by t, or m1 v1 minus m1 u1 is equal to minus m2 v2 plus m2 u2, or m1 v1 plus m2 v2 is equal to m1 u1 plus m2 u2. Now, m1 u1 plus m2 u2 is the total momentum before collision, whereas m1 v1 plus m2 v2 is the total momentum after collision. Therefore, we can say that the sum total of momentum does not change or is conserved. This is exactly what the law of conservation of momentum states. Newton's second law. Definition of Newton's second law. The rate of change of momentum of a body is directly proportional to the applied unbalanced force and takes place in the same direction in which the force acts. Mathematical expression for Newton's second law of motion. Consider a body of mass m at point A, such that its initial velocity is u. Let the body be acted upon by a force F for time t seconds, such that at B its final velocity is v. Let A be the acceleration of the body during the change in velocity. Now, initial momentum of the body at A is equal to mu. Final momentum of the body at B is equal to mv. Therefore, change in momentum of the body in time t is equal to mv minus mu. Or change in momentum of the body in 1 second is equal to mv minus u divided by t. But the change in momentum of the body in 1 second is equal to rate of change of momentum of the body. Therefore, rate of change of momentum of the body is equal to mv minus u divided by t. Statement 1. Also, we know v is equal to u plus at. Therefore, a is equal to v minus u divided by t. Statement 2. Putting the value of statement 2 in statement 1. Rate of change of momentum of the body is equal to ma. Statement 3. Now, the Newton's second law of motion. Rate of change of momentum of the body is proportional to F impressed unbalanced force. Statement 4. Comparing statement 3 and statement 4. F is proportional to ma, or F is equal to K into ma. Statement 5. K is constant of proportionality. If there be a body having a unit mass and unit acceleration, such that the force possessed by it is 1 unit, then 1 is equal to K into 1 into 1, or K is equal to 1. Statement 6. Putting the value of K in statement 5, we have F is equal to 1 into ma. F is equal to ma. Newton's third law of motion. Definition. To every action, there is an equal and opposite reaction. Or, whenever a given body exerts some force on another body, second body, then the second body exerts an equal and opposite force at the same time on the first body. Explanation. Let us consider a ball placed on the ground. It exerts force W due to its weight. It tends to thrust itself into the ground, but the ground offers an equal and opposite reaction R to the force exerted by the ball. Thus, the force exerted by the ball is balanced by the reaction of the ground on the ball, and the latter remains in its original position on the ground. Practically, in all cases of motion, it is the reaction which plays an important part. When we walk, our feet push the ground backward and the reaction acts in the opposite direction. This reaction makes us move forward. Examples where Newton's third law of motion comes into play. When a boatman pushes the bank of the river with the pole in the backward direction, the bank offers an equal and opposite reaction, which makes the boat move in the forward direction. It becomes difficult to walk on a sandy beach because when we push the sand backward with our feet, the sand yields. Thus, it does not react back with the same force. Thus, walking forward becomes difficult. It is for the same reason that we cannot swim in water as fast as we can run on the ground. It is because the water yields when we push it backward with our hands. The boatman always ties his boat before allowing the passengers to disembark. It is because when the passenger starts disembarking, they push the boat backward with their feet. Since the boat is in water and the water yields under the impact of a force, therefore the boat has a tendency to slide back in water. To avoid sliding of boat backward into the water, the boatman ties the boat. Feather and coin experiment. Materials required: feather, a coin, a long glass tube,
Vacuum pump.
Procedure. We know that almost all bodies near the surface of the earth fall towards the earth when released. However, earlier it was thought that the heavier bodies fall towards the earth more rapidly than the lighter bodies. The familiar example was that of a feather and a coin. It was noticed that the coin falls towards the earth more rapidly than the feather when dropped from the same height. However, Galileo did not agree with the idea that the heavier body, the more rapidly it falls towards the earth. He dropped one stone and a feather of different masses from the Leaning Tower of Pisa, and showed that they reached the earth at the same time. He explained that the feather took a longer time to reach the earth because it had a large surface area and hence encountered more resistance due to the air as compared to coin. The feather slowed down due to air resistance and not because it has a smaller mass. Later on, Robert Boyle created vacuum in a long glass tube and then allowed the feather and the coin to fall simultaneously. He showed that both of them reached the bottom of the tube at the same time, thereby proving Galileo right. Thus, to conclude, we can say that acceleration produced in freely falling bodies is the same for all bodies irrespective of their masses. To study the effect of thrust on a body in relation to its area of contact with another body. Materials required: a wooden cone about 12 cm long such that area of broad end is 5 cm square or more and area of smaller end is 1 cm square or less. Large amount of wet sand, 1 kg weight or a brick. Procedure. Spread the wet sand on the floor such that its layer is 3 cm thick or more. Now, place the cone on the sand such that its broad end is in contact with the sand. Gently place 1 kg weight on the narrow end of the cone. Remove the cone and measure the depression produced in the sand. Repeat the activity with the narrow end of the cone. You notice that in this case, the depression formed is more than that produced by broad end. Now, the question arises, when same compressive force is applied, why the depression produced by the broader end of the cone is smaller than the depression produced by the narrow end of the cone? Well, the effect of compressive force, thrust, is different because of the difference in the area of cross-section of cone in contact with the sand. This effect of thrust on a given area of cross-section is called pressure. To show the existence of upthrust or buoyant force. Definition: the upward force experienced by a body when partly or wholly immersed in a fluid is called upthrust or buoyant force, whereas the phenomena responsible for this force is called buoyancy. Materials required: an empty sealed tin, a bucket half filled with water, 20 ground force weights, brine solution. Procedure: take an empty sealed tin and place it in a bucket half filled with water. You notice that tin floats. Why does the tin float in spite of the fact that force due to gravity is pulling it downward? Obviously, the tin experiences an upward force, upthrust, which must be equal to the weight of the tin. Now place 20 ground force weight on the top of tin. You observe that tin will move deeper in water, but continues floating. Repeat the experiment with a few more 20 ground force weights. You observe that tin continues moving down in water till it is completely immersed. Remove the weights one by one. You observe that tin starts rising upward. Repeat the experiment by using brine solution, saturated solution of common salt. Observation: the initial length of the tin in brine solution is less than that in water. The brine solution can support more 20 ground force weights than water, till it is completely immersed in brine solution. Conclusions drawn regarding upthrust. When a body is immersed in a fluid, it always experiences an upthrust. The magnitude of upthrust increases with the increase in volume of a body immersed in fluid, and hence with the increase in fluid displaced by the body. The magnitude of upthrust increases with the increase in the density of fluid. It means more the density of a fluid, more is the upthrust, and vice versa. When a body is floating on its own in a fluid, there is an equilibrium state. It means weight of the whole body acting vertically downward is equal to upthrust produced by the liquid displaced by the immersed part of the body. The apparent weight of the body completely immersed in fluid will always be less than its actual weight because of the upthrust. Even when we weigh a body in air, the weight recorded will be apparent weight and not true weight, because the air being a fluid also produces upthrust. Verification of Archimedes' principle. Materials required: spring balance 0 to 100 ground force, glass stopper about 50 gram, brass weight 50 gram, thin cotton thread, overflow jar, wooden block, pre-weighted beaker 37 ground force, 250 cc beaker containing tap water. Procedure: take a clean glass stopper and tie it to a fine thread. Make a loop on the other end of cotton thread. Check the spring balance for zero error and record it. Zero error in the spring balance equal to 4 ground force. Suspend the glass stopper from the hook of the spring balance. Read and record its weight in air. Observe weight of glass stopper in air is equal to 48 ground force. Place the overflow jar on the wooden block and slowly pour in it tap water till the water just starts overflowing through its spout. At this moment, stop pouring the tap water. In a few moments, the water from spout stops overflowing. In this situation, the water in the overflow jar is at the verge of overflowing. Place the clean and dry pre-weighted beaker under the spout of the overflow jar. Weight of beaker is equal to 37 ground force. Now, gently lower the glass stopper into the water in the overflow jar till it gets completely immersed. It is noticed that as the glass stopper goes underwater, the spring balance registers less weight. Also, at the same time, the water overflows through spout and collects in the measuring pre-weighted beaker. Read and record the weight of glass stopper when fully immersed underwater. Observed weight of glass stopper in water is equal to 30 ground force. Weigh the pre-weighted beaker along with displaced water on the common compression balance. Weight of pre-weighted beaker plus displaced water is equal to 55 ground force. Observation and calculation. Zero error in spring balance is equal to 4 ground force. Observed weight of the glass stopper in air is equal to 48 ground force. Corrected weight of glass stopper in air is equal to observed weight minus zero error equal to 48 ground force minus 4 ground force is equal to 44 ground force. Weight of pre-weighted beaker is equal to 37 ground force. Observed weight of glass stopper in water is equal to 30 ground force. Corrected weight of glass stopper in water is equal to observed weight minus zero error is equal to 30 ground force minus 4 ground force is equal to 26 ground force. Therefore, apparent loss of weight of glass stopper in water is equal to corrected weight in air minus corrected weight in water equal to 44 ground force minus 26 ground force equal to 18 ground force. Weight of pre-weighted beaker plus displaced water is equal to 55 ground force. Therefore, weight of water displaced by glass stopper is equal to 55 ground force minus 37 ground force is equal to 18 ground force. It is noticed that loss of weight of glass stopper in water is equal to weight of water displaced by the glass stopper. Repeat the above experiment by immersing the glass stopper in the strongly salty water and brass weight in tap water and strongly salty water. You notice that loss of weight of glass stopper in salty water is equal to weight of salty water displaced by the glass stopper. Loss of weight of brass weight in water is equal to weight of water displaced by the brass weight Loss of weight of brass weight in salty water is equal to weight of salty water displaced by brass weight. Conclusion. It is clear that weight of water displaced by the glass stopper or brass weight is equal to apparent loss of weight of glass stopper or brass weight in water. This, in a way, verifies Archimedes' principle.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores. Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
To prepare stained temporary mount of onion peel and to record observations and draw their labeled diagrams. Requirements: onion, scalpel, forceps, slides, cover slip, watch glass, brush, saffronin, glycerin, blotting paper, water, microscope, scissors, dropper, and needle. Procedure: cut an onion into 4 to 6 pieces with the help of a scalpel. Take a fleshy succulent leaf and peel off a thin inner epithelial membrane with the help of a forceps. Put this portion of the onion peel in water in the watch glass. Transfer the peel from water on a drop of saffronin on a clean slide. Place the stained peel in clean water in a watch glass, again with the help of brush to wash off extra stain. Take a neat dry slide, add 1 or 2 drops of glycerin at the center of the slide. Transfer the stained epidermal peel with the help of brush onto the drop of glycerin carefully so that no air bubble should enter into the glycerin. Cover the glycerin with cover slip slowly. Care should be taken again to avoid the entry of air bubbles. Gently press the cover slip with needle so as to spread the glycerin evenly. Remove excess of glycerin using a blotting paper from the edges of the cover slip. Observe the slide under low power of microscope. Observations: in the portion of the epidermal peel to be examined, following observations are made. Large number of rectangular cells are observed separated by clear-cut cell walls having no air spaces. Darkly stained nucleus and lightly stained cytoplasm is observed in each cell. A prominent vacuole is seen in the center of each cell, making the cytoplasm peripheral where nucleus is present. Comment: the cells under observation are the plant cells due to the presence of large vacuole in the center and clear cell wall. To study the parts of a simple flowering plant. Requirements: freshly uprooted petunia plant, hand lens, a trough half filled with water. Procedure: dig out a small-sized flowering plant of petunia. Wash the complete plant with intact roots with water. Put it on the table with a sheet of paper beneath it. Spread all the parts carefully and study each part one by one. Draw the diagram of the complete plant and then draw each part separately. Label the diagrams and write comments. Observation and comments. The entire plant body comprises of a root system and a shoot system. Root system. Root system consists of the main root or primary root which remains under the soil in normal conditions. It is non-green and seems to be an extension of the stem below. From the main root, the secondary or lateral roots arise. These further bear branches as tertiary roots and root hairs. The secondary roots with all its branches spread in all directions. Such a root system is called as taproot system. Shoot system. Shoot system is the portion of plant which is aerial, that is, remains above the ground in normal conditions. The stem has nodes and internodes. All the parts of the plants like leaves, flowers, buds, branches, etc. arise from the nodal areas of the stem. Internode is the portion of the stem between two successive nodes which does not bear any appendage. It is meant for longitudinal growth of the stem. There is a bud at the terminal end of the main axis of the stem. This is the terminal bud. Axillary buds are present in the axil of the leaf where it is attached to the stem. Leaf. The leaves arise from the nodes, making an angle with the stem or the branch. A leaf has a green, flat, expanded portion having veins and veinlets and a main midrib. It bears a bud in its axil. Flower. A flower is a specialized reproductive shoot. After a period of vegetative growth, some vegetative buds may get modified to give rise to a flower. To study the morphological characters of the flowering plant of China rose. Procedure. Study the plant as a whole. Remove each part to study its features. Observation and comments. Habit. A perennial shrub. Cultivated ornamental. Stem, woody, aerial, erect, branched, cylindrical, solid, glabrous and green. Leaf, alternately arranged, petiolate, simple, stipulate, ovate-shaped, serrate margin, acute apex, multicostate reticulate and glabrous. Inflorescence, solitary axillary or terminal. Flower, pedicellate, abracteate, complete hermaphrodite, bisexual, actinomorphic, cyclic, hypogynous, pentamerous, epicalyx present outside the calyx and mucilage present. Epicalyx 6 to 8, free, forming a whorl outside the calyx, green, linear and hairy. Calyx, sepals 5, gamosepalous, valvate aestivation, persistent, green. Corolla, petals 5, polypetalous, fused at the base with staminal tube, twisted aestivation, large, mucilaginous and red. Androecium, stamens indefinite, monoadelphous, filaments united to form staminal tube around the gynosium, staminal tube fused below the petals, anthers monothecous, dorsifixed, kidney-shaped. Gynosium, pentacarpellary, syncarpous, pentalocular, many ovules in each locule, ovary superior, exile placentation, style long and slender, passing through the staminal tube, stigma 5, knob-like. To study the morphological characters of flowering plant Petunia. Procedure. Take the flowering twig of Petunia. Study the complete twig. Then observe carefully all the parts separately. Observation and comments. Habit: small, herbaceous, ornamental herb growing in winter season. Root system: it has distinct root system with prominent primary root and lateral branches. Shoot system: it consists of herbaceous, aerial, erect, branched, cylindrical, solid, hairy and green stem. Leaf: these are small and simple, having small petiole, exstipulate, shape ovate, margin entire. Acute apex, unicostate, that is one distinct midrib, reticulate venation and hairy. Inflorescence: flowers are found in groups, cymose, inflorescence. Flower: variously colored, purple, white, pink, pedicellate, bracteate, complete, bisexual, regular or actinomorphic, hypogynous and pentamerous. calyx, sepals 5, gamosepalous, hairy and persistent. Corolla, petals 5, gamopetalous, white, pink or purple. Campanulate or bell-shaped corolla. Androecium, stamens 5, free, epipetalous, united to the petals at the base, alternating with the petals, filaments long but unequal in length. Gynoecium consists of 2 united carpels, bilocular, many ovules in each locule, ovary superior, obliquely placed, placenta swollen, axile placentation, style long and stigma bilobed. To study the specimen of different types of underground stems for examination, identification, drawing and labeling of potato, onion, ginger and corm. Requirements: freshly dug out specimen of potato, onion, ginger and corm. Petri dishes and trough filled with water. Procedure: clean the freshly dug out material. Place them in the petri dishes. Observe them carefully. Observation and comments. Specimen 1. Potato. Botanical name: Solanum tuberosum. Tuber of potato is modified underground branch of the stem. The branch arises from the axil of a leaf on the main stem. The tip of this branch swells due to the accumulation of food and becomes a tuber. Each tuber is normally oval or rounded in shape. It consists of many nodes and internodes, but the nodes and internodes are not distinct. The nodes are demarked by the presence of scaled leaves and axillary buds or eyes. During favorable conditions, each eye can grow into a new aerial shoot and produce new tubers. At the end of the favorable season, the aerial shoots die and the tubers remain in the soil. The potato tubers are edible and used as vegetables. They also help in vegetative propagation. Specimen 2. Onion. Botanical name: Allium cepa. The bulb of onion is very much reduced underground stem. The bulb consists of a disc-shaped reduced stem and fleshy leaves growing from it. It is an example of tunicated bulb where fleshy scale leaves are present in concentric manner. These surround the central terminal bud. Fleshy scale leaves store food in the form of carbohydrates. Few outer leaves, which become dry and scaly, are protective in nature. Many adventitious roots arise from the underside of the disc. The points of origin of leaves represent the position of nodes. The apical bud develops into a flowering scape. Specimen 3. Ginger. Botanical name: Gingiber officinale. The rhizome is underground modification of the stem. It is a dorsiventral which grows horizontally under the surface of the soil. It stores food in the form of starch. It is branched, bears nodes and internodes. The nodes bear small-scale leaves with buds in their axil. During favorable conditions, the buds may grow into aerial shoots. The adventitious roots arise from the lower surface of the nodes. Specimen 4. Corm. Botanical name: Amorphophallus campanulatus. The corm is a modified stem. It is underground, swollen, fleshy and huge stem. It grows upright in position. It bears some scale leaves and adventitious roots. The corm is solid and fleshy due to accumulation of food. It is a condensed single internode which develops several daughter corms from adventitious buds. To study the specimens of germinating seeds of bean and maize for their examination, identification, drawing and labeling of the parts. Requirements: petri dishes, slides, dissecting needles, hand lens, specimens of the germinating seeds of bean and maize. Procedure: take soaked germinating seeds of bean and maize in separate petri dishes. Examine externally by using a hand lens. It will appear like this. Then gently remove the seed coat with the help of dissecting needles. By putting needles in between the cotyledons, open the seed to observe the embryo. It will appear like this. Observation and points of identification. Bean seed. Bean seed is a dicotyledonous seed and is X-albuminous. It is kidney-shaped and reddish-brown in color. On the concave side, there is an oval scar showing the point of the attachment of the ovule to the wall of the ovary or placenta, the hilum. A minute hole, the micropyle, is situated near hilum through which water and air can pass. On removal of seed coat, the harder testa and thin whitish tegmen, the two cotyledons, are seen. A tiny whitish axis, the embryo, having the radicle projecting out, is seen. With the help of magnifying lens, the embryo is seen to consist of plumule having a short stem and some small leaves, wide, thick, peg-like radicle. The plumule and radicle are the future stem and root of the plant. The bean seed shows epigeal germination. Maize grain. Maize grain develops from monocarpellary ovary. The pericarp is fused with the seed coat, therefore is actually a monocotyledonous one-seeded fruit called the grain. It is somewhat conical in shape and shows a light-colored oval area which marks the location of the embryo from outside. Vertical section reveals major portion of the grain occupied by starchy endosperm, whereas a small embryo is situated on one side at the base. The endosperm has outermost alurone layer which is proteinaceous. Due to the presence of endosperm, the grain is called as albuminous. The embryo consists of an upper shield-shaped scutellum which is actually the single cotyledon. It is separated from endosperm by an epithelial layer. The axis consists of radicle with its covering, the coleorhiza, and plumule with coleoptile on the lower and upper side respectively. Maize grain shows hypogeel germination. To prepare stained temporary mount of human cheek cells and to record observations and draw their labeled diagrams. Requirements: watch glass, slide, cover slip, needle, toothpick, methylene blue solution, blotting paper, microscope, glycerine, water in a beaker, and a dropper. Procedure: put a drop of water on a clean slide. Take a clean toothpick, scrape the inner side of the cheek. Scraping of the cheek should be done very carefully so that no damage is done. Put the epithelial scraping in a drop of water on a slide and spread it evenly so that the cells do not overlap. Put a drop of methylene blue on the drop of water. Remove excess of water and stain with the help of blotting paper. Cover the scraping with a drop of glycerine. Put a cover slip with the help of needle on the glycerine drop, taking care that no air bubble enters. Remove extra glycerine with the blotting paper. Overstaining and understaining should be avoided. Examine the slide under the microscope. Observations: the microscopic view shows a number of irregular cells. Distinct, deeply stained nucleus is seen in each cell. The cell wall is absent. Granular cytoplasm is bounded by thin plasma membrane. There are no intercellular spaces. Comment: the examination of the cells infers that they are animal cells, since there is no cell wall and central prominent vacuole is also not seen. To test the presence of glucose in a glucose solution. Requirements: glucose solution, test tubes, spirit lamp, test tube holder, freshly prepared Fehling's solution A and B, and Benedict's solution. Procedure 1. Mix approximately 1.5 ml of Fehling's solution A and 1.5 ml of Fehling's solution B in a test tube and note that it is unaltered. Now add equal amount of sugar solution and boil. Observation: brick red precipitate is formed. Explanation: the Fehling's solution contains cupric sulfate, sodium hydroxide and potassium sodium tartarate. When this solution is mixed with glucose and boiled, glucose is oxidized and cuprous oxide gives red precipitate. Procedure 2. Take about 3 milliliters of Benedict's solution in a test tube and add about 1 milliliter of glucose solution. Warm the mixture gently until a red-brown color appears. Observation and conclusion. The color of mixture changes from blue to green and finally rust brown, indicating the presence of reducing sugars. Explanation: Benedict's solution contains copper sulfate. When alkaline solution of sugars is added to copper sulfate, it gives rust brown color due to the formation of cuprous oxide.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
To test the presence of starch solution. Requirements: test tube, starch suspension, iodine solution, dropper, test tube holder, spirit lamp. Procedure: take a few milliliter of starch suspension in a test tube and add a few drops of iodine solution. Observe the change in color. Observation and conclusion. The color of the mixture changes to blue-black, showing the presence of starch. The blue-black color disappears on boiling and reappears on cooling. Explanation: starch molecules form a starch-iodine complex with iodine, which is blue in color. To test the presence of proteins. Requirements: protein solution, 1% copper sulfate solution, 40% sodium hydroxide, concentrated HNO3, concentrated NaOH solution, spirit lamp, test tubes, water in a beaker, dropper, test tube holder. Procedure 1. Add about 2 ml of 1% copper sulfate solution and 40% sodium hydroxide in some protein solution. Stir the mixture well to mix the content thoroughly. Note the change in color. Observation and conclusion. Pale purple or pink color appears, showing the presence of proteins. Procedure 2. Take about 3 ml of protein solution in a test tube and add equal amounts of concentrated HNO3. A cloudy white precipitate appears, which turns yellow on boiling. Cool the test tube in beaker filled with water and then add concentrated NaOH to make the mixture neutral and then to alkaline. Observation and conclusion. Yellow color turns to orange, showing the presence of proteins. To test the presence of fats and oils. Requirements. Test tube rack, test tube, olive oil, water, petroleum ether, Sudan 3.5% in 70% alcohol, a piece of paper, and butter. Procedure 1. Pour a little amount of olive oil in a test tube and add a few drops of Sudan 3 to it. Oil turns red on shaking. Now divide the mixture into 2 test tubes equally. Add water into one and petroleum ether into the other. Shake well and observe. Observation and conclusion. Colored oil when mixed with water forms a distinct red colored ring over the surface of water. This shows the presence of oil which is not soluble in water. But when petroleum ether is added into oil, petroleum solution is formed. Thus, it shows that oil is soluble in petroleum ether. Procedure 2. Rub a piece of butter on a piece of paper. The spot where the oily substance was rubbed turns translucent, showing the presence of oil in the material used. Examination and identification of animal specimens belonging to the following groups of animals. Example: Porifera, Coelenterata, Annelida, Platyhelminthes, Arthropoda, Pisces, Amphibia, Aves, and mammals. Requirements. preserved laboratory specimens of sponge, hydra, tapeworm, earthworm, moth, prawn, bony fish, frog, toad, pigeon, rat, and bat. Procedure. Study the preserved specimen carefully, draw, label the diagram, and write the comments. Specimen 1. Sponge. Sponge belongs to phylum Porifera. The phylum includes animals with pores all over their body, with one large opening called the osculum. There is no head, trunk, or tail. There are no bones, but body has a peculiar canal system for circulation of water. Organ systems are absent. Skeleton is made up of calcareous or siliceous spicules or proteinaceous spongin fibers. Reproduction is both by sexual and asexual methods. Specimen 2. Hydra. Hydra belongs to phylum Coelenterata. It is a fresh water animal found attached to submerged rocks, etc., but it gets itself detached to move freely for some time. Coelenterates are characterized by the presence of a hollow cavity called the coelenteron with a sticky basal disc called pedal disc. Hydra shows bilateral symmetry. There is tissue-level organization showing division of labor. Hydra is diploblastic animal having two germinal layers with a non-cellular layer, mesoglia, in between the two. A number of tentacles are present encircling the mouth, which are used to capture food and for defense. There are peculiar cells, the stinging cells called nematocytes, present on the tentacles. Specimen 3. Tapeworm. These animals are commonly called as flatworms belonging to phylum Platyhelminthes. Tapeworm is bilaterally symmetrical and dorsoventrally flattened. The animals are the triploblastic, that is, having three germinal layers: ectoderm, mesoderm, and endoderm. Tapeworm is acoelomate, that is, the body cavity or coelom is absent. These are endoparasites. The body is long tape-like, made up of units called segments, joined end to end. The anterior end attaches itself to the wall of intestine with the help of scolex, the head. The head is followed by neck, which leads to a long body. The animal is hermaphrodite. Eggs are produced in large numbers. Life cycle is completed in two hosts, primary host being man and the secondary host the pig. Specimen 4. Earthworm. Earthworms are regarded as farmers' friends. They belong to phylum Annelida. The body shows bilateral symmetry. Earthworm has long cylindrical body and is divided into segments. It is a burrowing animal living in moist soil. Mouth is a simple opening at the anterior end. It has an anal opening at the posterior end. A hard girdle-like glandular band is present in the segments 14 to 16 called the clitellum. It helps in cocoon formation during reproduction. Earthworm is hermaphrodite. Setae are present on the body which help the animal in locomotion. Specimen 5. Moth. Moth belongs to the phylum Arthropoda. The body is divided into head, thorax and abdomen. Thorax bears 3 pairs of joined legs and 2 pairs of wings. The body is covered by minute scales. The mouth parts are sucking type. Feathered antennae are present on head. Metamorphosis is complete. The cocoon yields silk thread which is of great economic importance. Sexes are separate. Moth is nocturnal. Specimen 6. Prawn. Palimon. Prawn belongs to phylum Arthropoda. The body is divided into 2 parts, anterior cephalothorax and posterior abdomen. It bears jointed appendages. The head bears 2 pairs of antennae. It has stalked compound eyes. The cephalothorax is formed by union of head having 5 segments and 8 segments of thorax. Abdomen is comprised of 6 distinct movable segments ending up in terminal segment, the telson. A pair of jointed appendages are present on each segment. Legs on thorax bear claws. Specimen 7. Bony fish. Rohu, salmon, etc. The fish belongs to phylum Chordata and class Pisces. The body is streamlined, that is boat-shaped. The body is covered by overlapping scales. The fish has paired pectoral and pelvic fins. 3 or 4 unpaired fins are also present. 2 lateral lines regarded as sense organs are present on the 2 lateral sides of the body. 2 large eyes with no eyelids present on the head. Nostrils are present, but they are functionless. External ears are absent. Operculum covers the gill slits. Endoskeleton is bony. Specimen 8. Frog. Frog belongs to phylum Chordata, class Amphibia. They have terrestrial mode of life, that is, can live in both land and water. These are cold-blooded animals and are carnivorous. Frog has moist, slippery skin due to the presence of mucus. Frog carries on with 3 types of respirations: buccal, pulmonary and cutaneous respiration. Frog has broad triangular head bearing wide mouth, 2 bulging eyes having 3 eyelids and nostrils. It has no neck and tail. Limbs bear small fingers. Hind limbs are long and webbed. Specimen 9. Toad. It belongs to phylum Chordata, class Amphibia. The skin is rough, warty, supplied with poison gland, forelimb secreting milky poisonous secretion. Forelimbs are shorter. Poison gland is present behind tympanum. Nocturnal in habit and is a carnivore. Specimen 10. Pigeon. Pigeon belongs to phylum Chordata and class Aves. The skin is covered with feathers which help it to fly and keep its body warm. Body is divided into head, thorax and abdomen. Forelimbs are modified into wings. Hind limbs are meant for walking, swimming, perching, etc. Since it is an aerial animal, the bones of the skeleton are hollow and light. It is a warm-blooded animal. It has a horny beak but no teeth. It has a 4-chambered heart. Specimen 11. Rat. Rat belongs to phylum Chordata, class Mammalia. Animals belonging to class Mammalia are most advanced, having highest developed brain. Skin is covered with hair. External ear or pinna is present. Mammary glands are present. Teeth are lodged in sockets and are of different types. Sexes are separate. Fertilization is internal. They give rise to young ones viviparous. Specimen 12. Bat. It belongs to phylum Chordata and class Mammalia. Skin is covered with hair. Mammary glands are present. Forelimbs are modified into wing-like structures, making it a flying mammal. It has large projecting external ears, pinna. Examination of the general anatomy of a mammal, example rabbit. Requirements: a chart showing general anatomy of rabbit. Procedure: observe the chart, draw, label and write comments on the same. Observation and comments. It is observed that internally the body cavity or coelom is separated by a muscular partition called diaphragm in two unequal parts, the anterior thoracic cavity and the posterior abdominal cavity. There are a number of organs present in the body cavity which are referred to as the visceral organs. Some of the organs are trachea with lungs, a muscular heart, stomach, liver, small intestine, kidneys, large intestine, and testes or ovaries.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
Identification of the structure of the following organs through specimens, models and charts: kidney, lung and heart. Requirements: a chart of the structures of organs of mammals, human. Observation and comments. Kidney. External structure. Kidney is a bean-shaped structure. It is dark brown in color, each about 11 cm long, 6.5 cm broad and 2.5 cm thick. Inner margin of the kidney is concave and is called hilum. Blood vessels and ureters have the kidney through it. Internal structure. LS of kidney shows two main regions, outer cortex and inner medulla. Cortex. It is dark red in color and is covered by a fibrous capsule. Medulla. It is light red in color and subdivided into conical renal pyramids. The apex of each pyramid has papilla which projects into the pelvis. Each kidney is composed of about 1 to 2 million uriniferous tubules or nephrons, the functional units of kidney. Lung. External structure. The lungs are a pair of spongy, elastic organs. The right lung is 3-lobed, while the left one is 2-lobed and slightly smaller to accommodate the heart. Each lung is enclosed by two membranes, outer parietal pleura and inner visceral pleura. Internal structure. Each alveolus or air sac is covered by capillary network of pulmonary artery and vein. Alveoli have very thin membranes of squamous epithelium which helps in exchange of gases between alveolar air and blood capillaries. Heart. External structure. Heart is hollow, muscular, cone-shaped organ. It is about the size of a fist and weighs approximately 300 grams. It is enclosed in a membranous sac called pericardium. Pericardial fluid flows between the membranes, protecting the heart from shocks, injury, and friction, also keeping the latter warm. Internal structure. Heart has 4 chambers, 2 auricles and 2 ventricles. Auricles are 2 upper chambers, left and right, thin-walled and separated by interauricular septum. The walls of auricles are thin. Right auricle receives deoxygenated blood from the body by 2 large veins. Ventricles are 2 lower chambers, thick-walled and separated by thick interventricular septum. Right ventricle, however, has thinner wall. The right ventricle pumps blood to lungs through pulmonary artery and left ventricles supply blood to the body through aorta. Identification of different type of blood cells under the microscope. Requirements. Permanent slides of the cells of blood. Microscope. Observation and comments. The permanent slides of blood show the following features. Erythrocytes or red blood corpuscles, RBC. They are red in color, large in number, biconcave disc-like structures and enucleated. Leukocytes. Fewer in number as compared with RBC, bigger in size than RBC, colorless, irregular or oval in shape. They are of 2 major kinds. Granulocytes, having distinct granules in the cytoplasm, and agranulocytes do not have granules. Granulocytes are of 3 kinds. Eosinophils, they have bilobed nucleus. Cytoplasmic granules stain orange-red with acid dye eosin, engulf particles, and they are 60 to 300 per milliliter of blood. Basophils. Nucleus has 2 or more lobes, affinity for basic dyes and stain blue-black with them, found in small numbers of 35 to 100 per milliliter of blood. Neutrophils. Nucleus is polymorphic with 3 to 5 lobes, found in large number of 400 to 500 per milliliter of blood, stain with neutral dyes and are phagocytic in nature. Agranulocytes. Lymphocytes. Small blood cells with large indented nucleus, number ranging from 1500 to 2000 per milliliter of blood. They are irregular in shape, migrate through the walls of the blood capillaries into the tissues by the process of diapedesis. Monocytes. They are bigger cells having larger cytoplasm. Nucleus is kidney-shaped. 200 to 700 per milliliter of blood in number and are phagocytic in nature. To demonstrate the mechanism of breathing. Requirements. A glass bell jar, rubber sheet, Y-shaped glass tube, 2 balloons, string, rubber cork. Procedure. Fix up the Y-shaped glass tube with the balloons in the bell jar. Tie the thin rubber sheet around the bottom of the bell jar with the string. The sheet of the rubber tied round the bottom edge of the bell jar represents the diaphragm. The two balloons represent the lungs. The space inside the bell jar, the thoracic cavity, and the white tube represent the trachea bifurcating into two bronchi. When the sheet of rubber is pulled downwards, the balloons expand due to air rushing in through the tube at the top. When the sheet is pushed upwards, the balloons collapse again due to the air rushing out. Inference. The experiment demonstrates the mechanism of respiration due to the increase and decrease of the thoracic cavity area by the movement of diaphragm and aided by the movement of the rib cage.
To prepare stained temporary mount of onion peel. Materials required: medium-sized onion, slide, cover slip, watch glass, forceps, knife, needle, distilled water, glycerine, dropper, blotting paper, saffron in solution, compound microscope, brush. Procedure. Take a medium-sized onion and cut it laterally into 4 to 5 pieces with the help of a knife. Remove a scale leaf from one of the pieces. Break the scale leaf gently from the middle and peel a small portion from the delicate epidermis, that is the covering, that covers the inner surface of the scale leaf. Remove the delicate epidermal peel with the help of forceps and place it in a watch glass containing distilled water. Take another watch glass and place in it 3 to 4 drops of saffron solution. With the help of brush, transfer the peel in water into the saffron solution for staining. Wait for 2 to 3 minutes. Transfer the peel back to the watch glass containing water. This will remove the extra stain sticking to the peel. Take a clean glass slide and pour 1 to 2 drops of glycerine. Transfer the stained peel on the drops of glycerine on the slide with the help of brush. The peel may tend to curl up. With the help of needle and brush, flatten the peel. Place the cover slip on the slide in such a way that no air bubbles enter in it. Gently press the cover slip with needle to spread glycerine and peel properly. Remove the extra material surrounding the slide with the help of blotting paper. Examine the slide under compound microscope. Observation. There are large number of cells lying side by side with distinct cell walls. A largely stained nucleus is present in the periphery of cytoplasm. A lightly stained cytoplasm is the periphery of cell wall. A prominent vacuole is the center of each cell, surrounding by cytoplasm. Inference. The cells under observation are the plant cell. It's because cell wall and large vacuoles are clearly seen.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
To prepare stained temporary mount of human cheek cells. Materials required: slide, cover slip, toothpick, glycerine, methylene blue solution, blotting paper, compound microscope, dropper, water. Procedure: take a clean slide and in the middle of it pour a drop of water with the help of a dropper. Take a clean toothpick and use it to scrape the inner wall of your cheek gently so as to scrape the epithelial tissue. Mix the scrap on the toothpick in the drop of water placed on the slide. Pour a drop of methylene blue solution on the mixture on the slide and mix it thoroughly. This will stain the epithelial tissue. After 2 to 3 minutes, remove the excess of water and methylene blue solution by using the corner of a blotting paper. Do it carefully, otherwise the material will also be removed. Pour a drop of glycerine on the contents of slide and spread it. Take a dry and clean cover slip and place it on the slide. Remove the extra material surrounding the slide with a blotting paper. Examine the slide under a compound microscope. Observation: large number of flat cells with irregular boundaries are seen. Each cell has a thin cell membrane. A distinct, deeply stained nucleus is seen in each cell. Space between the plasma membrane and the nucleus is filled with granular material called cytoplasm. There are no intercellular spaces between the cells. No cell wall is visible. Inference: the examination of material on the slide suggests that it is an animal cell because the cell wall and prominent vacuoles are not seen.
To identify parenchyma and sclerenchyma tissues in plants, striped muscles fibers and nerve cells in animals from prepared slides, and to draw their label diagrams.
Materials required: permanent slides of parenchyma tissues, sclerenchyma tissues, striped muscle fibers, and nerve cells. Compound microscope. Procedure: observe the permanent slides one by one under a compound microscope. Observation: 1. Plant tissues. A. Parenchyma tissues. The slide shows numerous cells. The parenchymatous cells are isodimetric. From isodimetric, it implies that almost all cells are equal in length and width. At the corners of the cells are present intercellular spaces. Each cell possesses a large central vacuole. Each cell has peripheral cytoplasm with a prominent nucleus. Each cell has thin cell wall. Inference: parenchymatous cells make simple tissues. Parenchymatous cells are living cells and a precursor of all other cells. These cells are present in the soft areas of plants such as stems, leaves, roots, flowers and fruits. The important function of these cells is photosynthesis or storage or helping in flotation. B. Sclerenchyma tissues. Sclerenchymatous cells are dead cells. They have evenly thickened hard cell walls. They have very little or no protoplasm. They have hard lignified secondary walls. They can be divided into two types. A. Fibrous sclerenchyma. B. Sclerides. Fibrous sclerenchyma. 1. They are highly elongated, narrow and spindle-shaped with pointed end walls. 2. Adjacent fibers have simple oblique pits. 3. The only function they perform is to provide mechanical strength. Otherwise, these fibers are empty and dead. Sclerides. 1. They are highly thickened, dead sclerenchymatous cells which have very narrow cavities. 2. They may occur singly or in groups and are isodimetric in nature. 3. They are sometimes called grit or stone cells. They provide stiffness to the plant wherever they occur. Inference. The sclerenchymatous cells, being thick-walled and having deposition of lignin, give mechanical strength to the plant. 2. Animal tissues. A. Striped muscle fibers. The slide shows large number of long cylindrical fibers that are enclosed in a membrane called sarcolemma. The fibers are non-tapering and wide. The fibers are multinucleated. The nuclei lie towards the periphery of the fibers. The cytoplasm of each fiber is called sarcoplasm. It is divided into large number of myofibrils. Each myofibril bears alternate light and dark band. Thus, these cells show longitudinal and transverse striations. The cells are surrounded and held by connective tissue. Inference. The observation of slide shows the presence of striated muscles. It is because they are long cylindrical fibers having myofibrils which make striations tightly packed. The muscles give contractibility and strength to the voluntary muscle. These muscles work according to our will. They get tired when overworked. B. Nerve cell. A nerve cell or a neuron has a large body called cyton. The cyton has a prominent nucleus. Cyton has cytoplasmic projections called dendrites. One of the dendrite is long and is called axon. A group of axons held together by a connective tissue is called a nerve. The axons are covered with medullary sheath or myelin sheath. At the nodes of Ranvier, the myelin sheath is absent. A membrane called neurilemma surrounds the sheath. The nerve endings are attached to muscles. Inference. From the above observation, it is clear that a nerve cell of a large cyton with a prominent nucleus such that Cyton has cytoplasm projections called dendrites. One of the dendrite is long and is called axon. The axons or fibers are packed together to make a nerve for the transfer of impulses. To test the presence of starch in the given food sample. Materials required: test tube, starch solution, that is, water extract from boiled rice, iodine solution, dropper, test tube holder. Procedure: take a few milliliter of starch solution in a test tube with the help of a dropper. Now, add a few drops of iodine solution to it. Observe the change in color of the mixture. Observation: the color of the mixture changes to blue-black. Inference: the color of given sample shows the presence of starch. To test the presence of the adulterant metanyl yellow in dal. Materials required: test tube, liquid boiled yellow dal, hydrochloric acid HCl, test tube holder, dropper. Procedure: take 5 milliliter of liquid boiled yellow dal in a test tube. Add a few drops of hydrochloric acid, HCl, keeping the mouth of the test tube away from your face. Ensure that you add hydrochloric acid drop-wise. Observation: a pink color appears in the test tube. Inference: the given sample of dal contains the adulterant metanyl yellow. To study the characteristics of Spirogyra, fern, pinus, and an angiospermic plant. A. Algae, Spirogyra. We can study the characteristics of Spirogyra by observing its permanent slide under a compound microscope. Characteristic features: 1. It is a filamentous algae. It grows in length, not in thickness, and is always one cell thick. Spirogyra is slimy to touch. 2. Spirogyra grows in fresh water bodies like lakes, ditches, ponds, etc. It is commonly called water silk due to its silk-like appearance. 3. It has a series of cells joined end to end to form a filament. Each cell has one or more spiral chloroplast from one end to another. 4. Small protein bodies called pyrenoids are present on each ribbon-like chloroplast. Nucleus is in the center, suspended by strands of cytoplasm. 5. There is a single large central vacuole. There is a thin gelatinous sheath around the cells. 6. Spirogyra breaks off after some distance in the filament into fragments. The fragments are capable of giving rise to a long filament by mitotic divisions. 7. Spirogyra reproduces sexually by conjugation. It occurs during favorable conditions. B. Fern. Dryopterus. Characteristic features. 1. There are about 12,000 named species of ferns ranging from small aquatic plants to giant tree ferns of tropical forests which may grow to over 30 to 40 feet. 2. They are found in humid tropical conditions, but some survive the subarctic conditions as well. 3. The plant body is a sporophyte which has true roots, stems and leaves with vascular tissue. The gametophyte is reduced to simple small prothallus. The plants exhibit alternation of generation with the sporophyte being dominant. 4. The stems of most ferns except tree ferns is an underground horizontally growing rhizome. The roots are adventitious which are produced from the rhizome. 5. The ferns may have different types of fronds or leaves. Simple leaves, leaves with one blade. Unipinnate, when the midrib bears the leaflets. Bipinnate, when the leaflets are further divided. Tripinnate, when the leaf is thrice pinnate. 6. In Dryopterus, the young leaves are coiled. They uncoil like a watch spring as they grow. C. Gymnospermic plants. Pinus, that is, male cone. Characteristic features. 1. Pine tree has one main axis of growth called monopodial growth. As the main axis, the trunk grows taller, it increases in diameter. 2. Pinus is common on temperate and tropical hills in India. Himalayas, the hills of Shimla and Missouri, have many of these tall, conical, evergreen, xerophytic trees. 3. The stem is thick, cylindrical, with long and dwarf branches. Long branches arise from the main trunk, show unlimited growth and are covered with scale leaves. Dwarf branches arise from scale leaves of long branches. These bear needle-like leaves. These are of limited growth. 4. Pinus has mycorrhizal taproots covered with fungal hyphae which help in water and mineral absorption. 5. Vascular system is well developed with xylem and phloem tissues. Resin canals are present in root, stem and leaves containing resins. 6. Pinus is a monoecious tree with both male and female cones. The reproductive structures. Male cone is smaller in size than the female cone. They borne in clusters behind apical buds of new shoots, that is, long branches. They have scale-like microsporophiles. 2 microsporangia are present on the ventral side of the microsporophile. Microsporangia release winged pollen grains which fly through air and reach eggs. D. Angiospermic plant, dicot, Brassica campestris. Characteristic features. 1. Brassica is a tall, cultivated, biennial herb of about 1 meter long. 2. It is a mesophytic land plant. Structure. 1. Root is a tap root. Stem is herbaceous and green. 2. Leaves are alternate, sessile, simple with lobed margins. They are dorsiventral and have netted veins. 3. Flower is yellow, has 4 petals, bisexual, stamens 6, 4 long and 2 short, ovary elongated. 4. Fruit is called siliqua, having an elongated capsule with replum, that is, false septum, which bears seeds. Seeds have 2 cotyledons.
To observe and draw the given specimens, earthworm, cockroach, bony fish and bird. For each specimen record, A. One specific feature of its phylum, B. One adaptive feature with the reference to its
Habitat. A. Earthworm. Characteristic features. Earthworm lives in soil and enters by burrowing it. Thus, the body is elongated, cylindrical and segmented, which helps in easy penetration into the soil. Anteriormost segment is modified into prostomium, which helps to eat and penetrate the soil as it moves into it. The earthworm feeds upon soil having rich organic matter, the humus. The color of earthworm is brown, which gives it protection against enemies. The skin is slippery and is kept moist as it respires through the skin. Mucus covers the skin, which does not allow soil to stick to its surface. The animal comes out of its burrows during the rainy season. Body is flexible, having no skeleton. Muscles help in locomotion and burrowing. B. Cockroach. Characteristic features. The body of cockroach is basically divided into 3 major portions: head, thorax and abdomen. The body is covered by exoskeleton, which gives it protection against enemies, as it is a terrestrial animal. Body is dorsoventrally flattened so that it can creep through even small crevices. It is omnivorous. It has to take up atmospheric oxygen, therefore, it has holes in thorax and abdomen for respiration called spiracles. They are of dark brown color as it helps them to hide away from enemies. They have antennae which are movable and help cockroach to sense the odor. The main characteristic feature of this phylum is joint legs or joint appendages. 3 pairs of joint legs are easily visible. C. Bony fish. Characteristic features. Fish belongs to phylum Chordata as it possesses strong vertebral column and strong endoskeleton to live in water and cut water current. To adapt aquatic mode of life, the shape of the body is streamlined. Fish respires with the help of gills. The fish always remains in water, thus its body is covered over by scales, thereby prevents decay. Fins help the fish to swim and change direction in water. Bony fish has air bladder to give it buoyancy. It detects the pressure of water with the help of lateral line. D. Bird. Characteristic features. The characters of birds are adapted for aerial mode of life. The body is streamlined. The body is covered by 3 kinds of feathers which help it to fly and keep the body warm. The forelimbs are modified into wings for flying. The hind limbs are meant for walking. Horny beak without teeth is present, which varies in size and shape according to the habit and habitat. The head is flexible, thus it can see various directions by its movement. Skeleton is made up of light hollow bones to give it buoyancy to fly. To determine the percentage of water absorbed by raisins. Materials required: dry raisins, small plastic jar half filled with water, weighing balance, and blotting paper. Procedure: weigh the dried raisins. Place the raisins in a plastic jar half filled with water. Allow the raisins to get soaked for 24 hours. After 24 hours, take out the swollen raisins from the water and gently dry them in the folds of blotting paper. Weigh the raisins again. Calculation: weight of dry raisins X equals 30 grams. Weight of swollen raisins Y equals 60 grams. Weight of water absorbed by the raisins equals Y minus X equals 60 minus 30 equal to 30 grams. The percentage of water absorbed by raisins equals Y minus X into 100 upon X equals to 60 minus 30 into 100 upon 30 equals to 30 into 100 upon 30 equals to 100%. So, the percentage of water absorbed by the raisins is 100%.
to identify a given gas by different methods. Examining color of the gas. Observation. The color of gas is deep reddish brown when hot and pale brown when cold. Inference. The gas may be nitrogen dioxide gas, NO2. Observation. The color of gas is greenish yellow. Inference. The gas may be chlorine, Cl2. Observation. The color of gas is colorless. Inference. The gas may be hydrogen, H2, oxygen, O2, ammonia, NH3, hydrogen chloride, HCl, sulfur dioxide, SO2, carbon dioxide, CO2, or water vapor, H2O.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
Examining odor of the gas. The odor of gas evolved is found by wafting the gas with the hand towards nose. Observation. Choking odor which causes pungent sensation in nasal cavity. Inference. The gas may be hydrogen chloride gas, HCl. Observation. The gas is of greenish yellow color and pungent odor. Inference. The gas may be chlorine gas, Cl2. Observation. The gas is reddish brown and has pungent and irritating odor. Inference. The gas may be nitrogen dioxide gas, NO2. Observation. The gas has a smell like rotten eggs. Inference. The gas may be hydrogen sulfide gas, H2S. Observation. The gas has a suffocating smell like burning sulfur and causes coughing. Inference. The gas may be sulfur dioxide gas, SO2. Observation. The gas has a sharp smell which brings tears in eyes. Inference. The gas may be ammonia gas, NH3. Observation. The gas has no odor. Inference. The gas may be oxygen gas O2, hydrogen gas H2, water vapor H2O, or carbon dioxide CO2. Effect of introducing lighted matchstick into the gas. Observation. The lighted matchstick is extinguished. Inference. The gas may be carbon dioxide, ammonia, sulfur dioxide, nitrogen dioxide, chlorine, hydrogen sulfide, hydrogen chloride, or water vapor. Observation. The lighted matchstick burns more brightly. Inference: the gas may be oxygen gas. Observation: the lighted matchstick goes off, but the gas burns with a pop sound. Inference: the gas may be hydrogen gas. Action with moist litmus paper. Observation: no change in moist blue and red litmus paper. Inference: the gas may be water vapor H2O, hydrogen H2 or oxygen O2. Observation: the moist red litmus paper changes to blue color. Inference: the gas may be ammonia NH3. Observation: the moist blue litmus paper changes to red color. Inference: the gas may be carbon dioxide CO2, hydrogen sulfide H2S, hydrogen chloride HCl or nitrogen dioxide NO2. Observation: the moist blue litmus paper changes to red color and then gets bleached. Inference: the gas may be chlorine Cl2 or sulfur dioxide SO2. To identify a given gas by different methods. Apparatus required: a rack of 6 clean test tubes, test tube holder, Bunsen burner, glass tube bent twice at right angles and provided with cork on its smaller limb, matchbox, dropper, red and blue litmus paper strips, plain filter paper strips, and a spatula. Chemicals required: zinc, dilute sulfuric acid, common salt dry, iron sulfide, dry ammonium chloride, lead nitrate, lime water, ammonia solution, freshly prepared ferrous sulfate solution, starch solution, distilled water, potassium chlorate, marble chips, sodium sulfite, dry calcium hydroxide, dilute hydrochloric acid, bleaching powder, acidified potassium dichromate solution, lead acetate solution, potassium iodide solution, potassium permanganate solution, concentrated sulfuric acid. Preparation of hydrogen gas H2. In a test tube, place 2 small pieces of zinc metal. With the help of a dropper, pour 2 cc of dilute sulfuric acid, taking care that no drop of the acid falls on the sides of test tube. Cover the mouth of test tube with your thumb till you feel the pressure of gas. Zn plus diluted H2SO4 forms ZnSO4 plus H2 gas. Now perform the test with the gas. Test 1. Note the color and odor of gas. Observation: the gas is colorless and odorless. Test 2. Moisten the blue and red litmus strips with distilled water and introduce them into the test tube. Observation: there is no change in the color of litmus papers. Test 3. Light a matchstick and take it near the mouth of test tube. Observation: the matchstick goes off and the gas burns with a pale blue flame with a pop sound. Preparation of oxygen gas O2. In a clean and dry test tube, place about 1 gram of potassium chlorate. Heat the test tube on a Bunsen flame till potassium chlorate melts. KClO3 forms 2KCl plus 3O2 gas. Note: the gas can be prepared by heating strongly potassium nitrate or sodium nitrate. 2KNO3 forms 2KNO2 plus O2 gas and 2NaNO3 forms 2NaNO2 plus O2 gas. Now perform the test with the gas. Test 1. Note the color and odor of the gas. Observation: the gas is colorless and odorless. Test 2. Moisten the blue and red litmus strips with distilled water and introduce them into the test tube. Observation: there is no change in the color of litmus papers. Test 3. Light a matchstick. When a part of it burns, put off its flame. Introduce this glowing matchstick in the test tube. Observation: the matchstick bursts into flame, but the gas does not catch fire. Preparation of carbon dioxide gas CO2. In a clean and dry test tube, place about 1 gram of marble chips. With the help of a clean dropper, pour about 2 cc of dilute hydrochloric acid, taking care that no drop of acid falls on the sides of the test tube. Cover the mouth of the test tube with your thumb till you feel the pressure of gas. CaCO3 plus 2HCl dilute forms CaCl2 plus H2O plus CO2 gas. Now perform the test with the gas. Test 1. Note the color and odor of gas. Observation: the gas is colorless and odorless. Test 2. Moisten the blue litmus strips with distilled water and introduce it into the test tube. Observation: the blue litmus paper turns weakly red. Test 3. Light a matchstick and take it near the mouth of the test tube. Observation: the matchstick goes off and the gas does not catch fire. Test 4. Pass the gas through about 2 cc of clear lime water in another test tube with the help of a bent glass tube. Observation: the lime water turns milky. CaOH2 plus CO2 forms CaCO3 white plus H2O. Preparation of hydrogen chloride gas HCl. In a clean dry test tube, place about 1 gram of sodium chloride. With the help of a clean dropper, pour about 2 cc of concentrated sulfuric acid, taking care that no drop of the acid falls on the sides of the test tube. Gently warm the contents of the test tube for half minute. NaCl plus H2SO4 concentrated forms NaHSO4 plus HCl gas. Now perform the test with the gas. Test 1. Note the color of the gas. Observation: the gas is colorless but fumes strongly in the air. Test 2. Note the odor of the gas. Observation: the gas has a choking odor which causes a pungent burning sensation in the nasal cavity. Test 3. Moisten a blue litmus paper with distilled water and introduce it into the test tube. Observation: the litmus paper turns red. Test 4. Light a matchstick and take it near the mouth of the test tube. Observation: the matchstick goes off and the gas does not catch fire. Test 5. Dip a glass rod in dilute ammonia solution and bring it near the mouth of the test tube. Observation: dense white fumes of ammonium chloride are formed. NH4OH plus HCl forms NH4Cl plus H2O. Preparation of sulfur dioxide gas SO2. Caution: this gas is poisonous. You may smell this gas. Do not inhale. In a clean and dry test tube, place about 1 gram of sodium sulfite. With the help of a clean dropper, pour about 2 cc of dilute sulfuric acid, taking care that no drop of the acid falls on the sides of the test tube. Close the mouth of the test tube with your thumb till you feel the pressure of the gas. Na2SO3 plus H2SO4 dilute forms Na2SO4 plus H2O plus SO2 gas. Now perform the test with the gas. Test 1. Note the color and the odor of the gas. Observation: the gas is colorless. The gas has a choking odor like that of burning sulfur and causes coughing. Test 2. Moisten a blue litmus paper with distilled water and introduce it into the test tube. Observation: the litmus paper turns red and then gets bleached. Test 3. Light a matchstick and take it near the mouth of the test tube. Observation: the matchstick goes off and the gas does not catch fire. Test 4. Take a filter paper strip and first dip it into potassium dichromate solution and then dilute sulfuric acid. Introduce this strip into the test tube. Observation: the orange-colored strip turns green. K2Cr2O7 plus H2SO4 plus 3SO2 form K2SO4 plus Cr2 SO4 whole 3 plus H2O. Preparation of chlorine gas Cl2. Caution: this gas is poisonous in nature. You may smell this gas. Do not inhale. In a clean and dry test tube, place about 1 gram of bleaching powder. With the help of a clean dropper, pour about 2 cc of dilute sulfuric acid, taking care that no drop of the acid falls on the sides of the test tube. Close the mouth of the test tube with your thumb till you feel the pressure of the gas. CaOCl2 plus H2SO4 dilute forms CaSO4 plus H2O plus Cl2 gas. Now perform the test with the gas. Test 1. Note the color of the gas. Observation: the gas has a greenish yellow color. Test 2. Note the odor of the gas. Observation: it has a pungent odor. Test 3. Light a matchstick and take it near the mouth of the test tube. Observation: the flame of the matchstick goes off and the gas does not catch fire. Test 4. Moisten a blue litmus paper with distilled water and introduce it into the test tube. Observation: the litmus paper turns red and then gets bleached. Test 5. Take a filter paper strip and first dip it into potassium iodide solution and then into starch solution. Introduce this filter paper strip into the mouth of the test tube. Observation: the filter paper strip turns blue. 2Ki plus Cl2 forms 2KCl plus I2. Starch plus I2 form blue color. Preparation of nitrogen dioxide gas NO2. In a clean and dry test tube, place about 1 gram of lead nitrate crystals. Hold the test tube in a test tube stand. Heat the test tube from below till the salt makes a crackling noise, decrepitating noise, and a colored gas comes out of it. 2PbNO3 whole 2 forms 2PbO plus 4NO2 gas plus O2 gas. Now perform the test with the gas. Test 1. Note the color of the gas. Observation: the gas has reddish brown color. Test 2. Note the odor of the gas. Observation: the gas has a suffocating smell. Test 3. Light a matchstick and take it near the mouth of the test tube. Observation: the flame of the matchstick goes off and the gas does not catch fire. Test 4. Moisten a blue litmus paper with distilled water and then introduce it in the test tube. Observation: the litmus paper turns red in color. Test 5. Take a filter paper strip and first dip it into potassium iodide solution and then into starch solution. Introduce this filter paper strip into the mouth of the test tube. Observation: the filter paper strip turns blue. 2Ki plus NO2 forms 2KNO2 plus I2. I2 plus starch solution form blue color. Preparation of hydrogen sulfide gas H2S. Caution: this gas is poisonous in nature. You may smell this gas. do not inhale. In a clean and dry test tube, place about 1 gram of crushed iron second sulfide. With the help of a clean dropper, pour about 2 cc of dilute sulfuric acid, taking care that no drop of the acid falls on the sides of the test tube. Close the mouth of the test tube with your thumb till you feel the pressure of the gas. FeS plus H2SO4 dilute form FeSO4 plus H2S gas. Now perform the test with the gas. Test 1. Note the color of the gas. Observation. The gas is colorless. Test 2. Note the odor of the gas. Observation. The gas smells like rotten eggs. Test 3. Moisten a blue litmus paper strip with distilled water and introduce it into the test tube. Observation. The litmus paper turns red. Test 4. Light a matchstick and take it near the mouth of the test tube. Observation. The flame of matchstick goes off and the gas does not catch fire. Test 5. Take a filter paper strip and dip it into the lead acetate solution. Introduce this strip into the test tube. Observation. The filter paper strip turns black. CH3COO Pb plus H2S form PbS plus 2CH3COOH. Test 6. Take a filter paper strip and dip it into the lead nitrate solution. Introduce this strip into the test tube. Observation. The filter paper strip turns black. PbNO3 plus H2S form PbS plus 2HNO3.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every concept, activity, experiment, example, or question given in the NCERT textbook. Scan to understand chapter-wise all types of questions as per latest CBSE exam pattern. Scan to understand every question given in CBSE, sample paper, and model test papers. Bringing learning at home, anytime, anywhere, any number of times. Making learning student-centric. Grab yours today from leading online platforms or nearby bookstores.
Preparation of ammonia gas, NH3. Prepare a mixture of about 1 gram of ammonium chloride and 1 gram of dry calcium hydroxide. Place this mixture in a dry hard glass test tube. Hold the test tube in a test tube holder. Heat the test tube from below by heating it over a low flame. Two NH4Cl plus CaOH whole 2 form CaCl2 plus 2H2O plus 2NH3 gas. After heating for about 2 minutes, perform the test with the gas. Test 1. Note the color of the gas. Observation. The gas is colorless but fumes strongly as soon as it enters in the air. Test 2. Note the odor of the gas. Observation. The gas has a sharp biting smell which brings tears to the eyes. Test 3. Moisten a red litmus paper with distilled water and introduce it into the test tube. Observation: the litmus paper turns blue. Test 4. Light a matchstick and take it near the mouth of the test tube. Observation: the flame of the matchstick goes off and the gas does not catch fire. Test 5. Dip a glass rod in concentrated hydrochloric acid. Hold the glass rod near the mouth of the test tube. Observation: dense white fumes of ammonium chloride are formed. NH3 plus HCl form NH4Cl. Test 6. Pour 1 cc of copper sulfate solution in another test tube. Pass the gas through copper sulfate solution by using a delivery tube bent at right angles. Observation: the copper sulfate solution initially forms bluish-white precipitate which redissolves to form deep blue coloration. Preparation of water vapor H2O gas. Take a clean and dry hard glass test tube and in it place about 2 grams of hydrated sodium carbonate or washing soda. Hold the test tube in a test tube stand. Heat the test tube from below for 3 to 4 minutes on a low flame in a slanting position. After 3 to 4 minutes, colorless drops of water collect on the upper cooler parts of it. Na2CO3 10H2O form Na2CO3 plus 10H2O gas. Now perform the tests with the droplets of water. Test 1. Place a strip of a blue litmus paper and red litmus paper on the droplets of water within the test tube. Observation: no change in color takes place in the litmus paper. Test 2. Place a strip of dry cobalt chloride paper on the droplets of water within the test tube. Observation: the color of cobalt chloride paper changes to pink. Test 3. Heat some crystals of copper sulfate blue strongly in a test tube till they form a white powdery mass of anhydrous copper sulfate. CuSO4 plus 5H2O form CuSO4 5H2O blue. Take a small amount of this white powdery mass, anhydrous copper sulfate, and pour it over the droplets of water within the test tube. The white mass changes to blue color. To heat the given unknown substance, make observations, identify products, and make deductions where possible. Copper carbonate, zinc carbonate, washing soda, copper sulfate crystals, zinc nitrate, copper nitrate, lead nitrate, ammonium chloride, iodine crystals, and ammonium dichromate. Apparatus required: a rack of clean and dry hard glass test tubes, test tube holder, Bunsen burner, tube bent twice at right angles having a cork with single hole on a smaller limb. Chemicals required: blue litmus strips, matchbox, clear lime water, distilled water, starch iodide paper, copper carbonate light green powder, zinc carbonate white powder, copper sulfate crystals, blue crystals, zinc nitrate, white crystalline solid, washing soda, white crystalline flake, lead nitrate, white crystalline solid, iodine crystals, steel grey crystals, ammonium dichromate, orange red crystals, copper nitrate, blue crystals, ammonium chloride, white crystalline solid. Test and observations for light green powder. Take a clean and dry hard glass test tube with test tube holder. Place a small amount of given substance, not more than 1 gram, in the test tube. Heat the test tube by holding it in slanting position such that its mouth is facing away from you. The lower end of the test tube should be held in the hottest part of the Bunsen flame. The substance is light green and amorphous in nature. Inference: the substance may be salt of copper or iron. On strong heating, it gives off a colorless gas. The colorless gas, on passing through clear lime water, turns it milky. The colorless gas turns moist blue litmus paper red. Inference: the gas evolved is carbon dioxide and the anion responsible for it is carbonate. The residue left is black in color. Inference: the substance is copper carbonate, CuCO3. CuCO3 forms CuO plus CO2 gas. Test and observations for white powder. Take a clean and dry hard glass test tube with test tube holder. Place small amount of given substance, not more than 1 gram, in the test tube. The substance is white, light solid and amorphous in nature. Inference: the substance may be salt of zinc metal. On strong heating, it gives off a colorless and odorless gas. When a burning matchstick is taken inside the gas, the flame gets extinguished. Inference: the gas may be carbon dioxide. When a moist blue litmus paper is held in the gas, it turns red. Inference: the gas may be carbon dioxide. When gas is passed through clear lime water, it turns the lime water milky. Inference: the gas is carbon dioxide and the anion responsible for it is carbonate. The residue in the test tube is yellow when hot. On cooling, the residue is white in color. Inference: the cation present in substance is zinc. The substance is zinc carbonate, ZnCO3. ZnCO3 forms ZnO plus CO2 gas. Test and observations for white flakes. Take a clean and dry hard glass test tube with test tube holder. Place small amount of given substance, not more than 1 gram, in the test tube. The substance is white crystalline solid in the form of flakes. Heat the test tube by holding it in slanting position such that its mouth is facing away from you. The lower end of the test tube should be held in the hottest part of the Bunsen flame. On strong heating, it swells and then melts. Steamy vapor gives off from it. The steamy vapor condenses on the cooler part of the test tube to form tiny droplets of a colorless liquid. Inference. The steamy vapor may be water of crystallization. The colorless liquid does not affect red litmus or blue litmus paper. Inference. The colorless liquid may be water of crystallization. The colorless liquid turns cobalt chloride paper pink. Inference. The colorless liquid is water of crystallization. On cooling, the molten residue partly fuses in glass and forms white amorphous powder. Inference. The white powdery mass may be anhydrous sodium carbonate. The substance may be washing soda, Na2CO3 10H2O. Na2CO3 10H2O forms Na2CO3 plus 10H2O.
Goyal Brothers Prakashan is pleased to introduce Digi Smart Books, a revolutionary learning experience through QR codes. Your teacher is just a scan away from you.
Hello students, we are going to start the chapter Real Numbers.
Scan to understand every
Crystals. Hold the clean and dry hard glass test tube with the test tube holder. Place small amount of given substance, not more than 1 gram, in the test tube. The substance is a blue crystalline solid. Inference. The substance may be salt of copper. Heat the test tube by holding it in slanting position such that its mouth is facing away from you. The lower end of the test tube should be held in the hottest part of the Bunsen flame. On strong heating, the blue crystals start crumbling, forming a white powdery mass. It gives off steamy vapor which condenses on the cooler parts of the test tube to form tiny droplets of the colorless liquid. Inference. The substance may be hydrated copper sulfate and the colorless droplets of the colorless liquid may be water of crystallization. The colorless droplets of the liquid do not affect red or blue litmus paper. Inference. The colorless liquid may be water of crystallization. The colorless droplets of the liquid turn cobalt chloride paper pink. Inference. The colorless liquid is water of crystallization. The substance is hydrated copper sulfate, CuSO4 5H2O. CuSO4 5H2O forms CuSO4 plus 5H2O. Test and observations for blue crystals or greenish blue crystals. Hold the clean and dry hard glass test tube with the test tube holder. Place small amount of given substance, not more than 1 gram, in the test tube. Heat the test tube by holding it in slanting position such that its mouth is facing away from you. The lower end of the test tube should be held in the hottest part of the Bunsen flame. The substance is blue or greenish blue solid crystalline in nature. Inference. The substance may be salt of copper. On heating, it melts to form greenish-blue mass and gives off steamy vapor, which condenses on the cooler parts of the test tube to form tiny droplets of a colorless liquid. The colorless droplets of the liquid do not affect red or blue litmus paper, but turn cobalt chloride paper pink. Inference. The steamy vapor is of water of crystallization present in the substance, and hence the substance is a hydrated salt. On strong heating, the substance gives off a reddish-brown gas. This gas turns moist blue litmus paper red. Inference. The gas may be nitrogen dioxide, which is acidic in nature. The gas turns moist starch iodide paper blue. Inference. The gas is nitrogen dioxide. When a glowing wooden splint is held in the gas, it bursts into flame. Inference. The reddish-brown gas also contains oxygen gas. The residue left in the test tube is black in color. Inference. The residue is of copper second oxide. The substance is hydrated copper nitrate, CuNO3(2) 6H2O. 2CuNO3(2) 6H2O form 2CuO plus 4NO2 gas plus O2 gas plus 12H2O gas. Test and observations for white crystalline solid. Hold the clean and dry hard glass test tube with the test tube holder. Place small amount of given substance, not more than 1 gram, in the test tube. The substance is heavy, white crystalline solid. Inference. The substance may be a salt of lead. Heat the test tube by holding it in slanting position such that its mouth is facing away from you. The lower end of the test tube should be held in the hottest part of the Bunsen flame. On strong heating, the crystals start crumbling with a crackling noise and give off a reddish-brown gas. Inference. The substance may be lead nitrate and the gas evolved may be nitrogen dioxide. When a glowing splint is held in the reddish-brown gas, it bursts into flame. Inference. The reddish-brown gas contains another gas, oxygen. When a moist blue litmus paper is held in the brown gas, it turns red. When a moist starch iodide paper is held in the brown gas, it changes into blue color. Inference. The reddish-brown gas is nitrogen dioxide. The residue in the test tube is reddish-brown when hot and changes to yellow color on cooling. It partly fuses in the test tube and stains it yellow. Inference. The residue is of lead second oxide. The substance is lead nitrate crystals PbNO3(2). 2PbNO3(2) form 2PbO plus 4NO2 gas plus O2 gas. Test and observations for white solid. Take a clean and dry hard glass test tube with test tube holder. Place small amount of given substance, not more than 1 gram, in the test tube. The substance is a light white crystalline solid. It tends to get wet when exposed to air. Inference. The substance is deliquescent in nature, maybe zinc nitrate. Heat the test tube by holding it in slanting position such that its mouth is facing away from you. The lower end of the test tube should be held in the hottest part of the Bunsen flame. On heating, the substance melts and gives off steamy vapor, which condenses on the cooler parts of the test tube to form tiny droplets of a colorless liquid. The colorless liquid has no effect on red or blue litmus paper. It turns cobalt chloride paper pink. Inference: the colorless liquid is water of crystallization and the substance is a hydrated salt. On strong heating, the substance gives out a reddish-brown gas. When a glowing splint is held in the reddish-brown gas, it bursts into flame. Inference: the reddish-brown gas contains another gas, oxygen. The reddish-brown gas turns moist blue litmus paper red. It turns moist starch iodide paper blue. Inference: the reddish-brown gas is nitrogen dioxide. The residue after strong heating is yellow when hot. On cooling, it changes to white color. Inference: the residue is zinc oxide. The substance is hydrated zinc nitrate, ZnNO3(2), 4H2O. 2ZnNO3(2), 4H2O form 2ZnO plus 4NO2 gas plus O2 gas plus 8H2O gas. Test and observations for white crystalline solid. Take a clean and dry hard glass test tube with test tube holder. Place small amount of given substance, not more than 1 gram, in the test tube. The substance is white crystalline solid, very light in weight. Inference: the substance sublimes, maybe ammonium chloride. Heat the test tube by holding it in slanting position such that its mouth is facing away from you. The lower end of the test tube should be held in the hottest part of the Bunsen flame. On strong heating, it forms dense white fumes. The dense white fumes condense on the cooler parts of the test tube to form white powdery mass. Inference: the ammonia gas and the HCl gas formed during its decomposition combine to form solid ammonium chloride. On heating continuously, the entire mass sublimes. It does not change into liquid state. Inference: the substance is ammonium chloride NH4Cl. NH4Cl forms NH3 gas plus HCl gas. Test and observations for steel grey crystals. Note: these crystals should not be touched with bare hands as they cause burns on the skin. Take a clean and dry hard glass test tube with test tube holder. Transfer a few crystals in a clean test tube with the help of spatula. Heat the test tube by holding it in a slanting position such that its mouth is facing away from you. The lower end of the test tube should be held in the hottest part of the Bunsen flame. On strong heating, they form beautiful violet vapor. The violet vapor condenses on the cooler parts of the test tube to form shiny steel grey crystals. Inference. The crystals of iodine, I2, sublime on heating to form gaseous iodine vapor, which is violet in color. I2 forms I2 vapor. Test and observations for orange-red crystals. Take a clean and dry hard glass test tube with test tube holder. Place small amount of given substance, not more than 1 gram, in the test tube. The substance is in the form of tiny orange-red crystals. Heat the test tube by holding it in slanting position such that its mouth is facing away from you. The lower end of the test tube should be held in the hottest part of the Bunsen flame. On strong heating, it swells up many a times its volume and gives off steamy fumes which condense on the cooler parts of the test tube to form tiny droplets of a colorless liquid. The liquid does not affect red or blue litmus, but it turns cobalt chloride paper pink. Inference. The colorless liquid is water, which is one of the products formed due to the decomposition of substance. On strong heating, the residue decomposes violently with flashes of light. A colorless and odorless gas is also given out. The gas has no action with moist red or blue litmus. Does not burn or help in burning, and does not turn lime water milky. Inference. The gas may be nitrogen. The residue left in the test tube is porous in nature and greenish-grey in color. Inference. The crystalline solid may be ammonium dichromate, NH4 Cr2O7. NH4 Cr2O7 form N2 gas plus 4H2O gas plus Cr2O3 solid. To identify the following anions or metals and make deductions on the addition of dilute sulfuric acid to unknown substance, warm if necessary. The unknown substance may be a sulfide ion, a carbonate ion, a metal such as magnesium, zinc or iron. Apparatus required: a rack of 6 clean test tubes, test tube holder, Bunsen burner, matchbox, glass tube bent twice at right angles and provided with cork on its smaller limb, dropper, red and blue litmus paper strips, plain filter paper cut in strips. Chemicals required: sodium sulfide solid, dilute sulfuric acid, lead acetate solution, lead nitrate solution, potassium dichromate solution, clear lime water, barium chloride solution, dilute nitric acid, sodium carbonate solution, sodium hydroxide solution, distilled water, dilute hydrochloric acid, magnesium strip, granulated zinc, solid sodium carbonate, iron filings. Detection of sulfide ions. Test 1. Take a pinch of salt, sodium sulfide, in a test tube and add about 2 milliliters of dilute sulfuric acid. Gently warm the solution. Note the color and the odor of the gas. Observation. A colorless gas with a smell like that of rotten eggs is evolved. Na2S plus dilute H2SO4 forms Na2SO4 plus H2S gas. Inference. The gas may be hydrogen sulfide. The anion present in the salt may be sulfide. Test 2. Repeat the experiment as in test 1 and hold a moist blue litmus paper in the gas. Observation. The blue litmus paper turns red. Inference. The gas is acidic in nature. Test 3. Repeat the experiment as in test 1 and hold a filter paper strip soaked in lead acetate solution in gas. Observation. The filter paper strip turns greyish. CH3COO Pb plus H2S forms 2CH3COOH plus PbS grey. Inference. Hydrogen sulfide gas is evolved. Sulfide ion is confirmed. Test 4. Repeat the experiment as in test 1 and hold a filter paper strip soaked in lead nitrate solution in gas. Observation. The filter paper strip turns greyish. PbNO3 plus H2S forms 2HNO3 plus PbS grey. Inference. Hydrogen sulfide gas is evolved. Sulfide ion is confirmed. Detection of carbonate ion. Test 1. Take a pinch of salt sodium carbonate in a test tube and add to it about 2 milliliter of dilute hydrochloric acid. Note the color and the odor of the gas. Observation. The reaction takes place with a lot of effervescence. A colorless and odorless gas is evolved. Na2CO3 plus dilute 2HCl form 2NaCl plus H2O plus CO2 gas. Inference. The gas may be carbon dioxide. Carbonate ion may be present. Test 2. Repeat the experiment as in test 1 and hold a moist blue litmus paper in gas. Observation. Litmus paper turns weakly red. Inference. Gas is acidic in character, may be carbon dioxide or sulfur dioxide. Test 3. Repeat the experiment as in test 1 and hold a filter paper strip soaked in acidified potassium dichromate in the gas. Observation. No change in color is observed on the filter paper strip. Inference. The gas is not sulfur dioxide. Gas may be carbon dioxide. Test 4. Repeat the experiment as in test 1 and pass the gas through about 2 milliliter of clear lime water in another tube with the help of a bent glass tube. Observation: lime water turns turbid. Inference: carbon dioxide is evolved. The anion may be carbonate. Test 5. Prepare the solution of salt sodium carbonate in distilled water. Take about 2 milliliter of salt solution and add to it same volume of barium chloride solution. Observation: a white precipitate appears. BaCl2 plus Na2CO3 form 2NaCl plus BaCO3 white precipitate. Inference: carbonate ion may be present. Test 6. To the precipitate in test 5, add dilute nitric acid in excess. Observation: the white precipitate dissolves to form a colorless solution. BaCO3 plus 2HNO3 form BaNO3 the whole 2 plus H2O plus CO2 gas. Inference: carbonate ion is confirmed. Detection of magnesium metal. Note: magnesium is a silvery white metal generally available in the form of strip. However, due to tarnishing or oxidation in air, it appears greyish in color with specks of white. Following tests can confirm whether the metal is magnesium or not. Test 1. To the small amount of a given metal, magnesium metal, add dilute sulfuric acid. Note the color and the odor of the gas. Observation: a very brisk reaction takes place with the evolution of a colorless and odorless gas. Magnesium plus dilute H2SO4 form MgSO4 plus H2 gas. Inference: the gas may be hydrogen. The metal may be magnesium, zinc or iron. Test 2. Repeat the experiment as in test 1 and hope the gas is hydrogen. Test 4. When the reaction in test 3 stops, remove the solution in another test tube.